51,000 citizens passed away. Just a few days after the earthquakes, UNESCO-Ipred suggested holding the regular annual meeting in Turkey because of this catastrophic event. After responding positively to this appreciated proposal, we started to work to perform this international conference. Today, it's my honor to introduce the international conference dedicated to the 6th February Kahramanmaraş earthquake, which includes 15 presentations from appreciated experts. Huge active faults activated by Kahramanmaraş earthquakes, the observations and lessons from the site, geotechnical and foundation engineering issues, responses of different types of buildings, infrastructure, facilities and historical monuments, Turkey, Japan and Chile earthquake cause are among the topics to be discussed during the day. Within the scope of UNESCO-Ipred, the conference will include participants from Algeria, Chile, Egypt, El Salvador, Indonesia, Kazakhstan, Mexico, Peru, Romania, Japan, France, England, America, China, and Turkey. The audience may have conversations with the guests coming from various earthquake-prone countries. I would like to thank all of you for attending to the conference. With my best regards.
Thank you, Professor Yüksel. On behalf of UNESCO, Mr. Amani Abu, Director of the Division of Water Sciences and Secretary of Intergovernmental Hydrological Program, will participate with his video message. Sorry, but the technical issues.
Excellencies, ladies and gentlemen. Excellencies, ladies and gentlemen, on behalf of UNESCO, Assistant Director General for Natural Sciences at ITÜ'nün, it is an honor and a pleasure for me to welcome you to this international conference on disaster reduction in the international platform for reduction earthquake disaster. I would like to thank Istanbul Teknik Üniversitesi for coordinating and organizing this event. I would also like to thank Japan for its generous financial support. May I begin by expressing my deepest condolences to the victims of the devastating earthquake which struck Turkey and the Syrian Arab Republic on 6 February this year. These earthquakes of magnitude 7.8 and 7.7 on the Richter scale respectively took approximately 53,000 lives and caused $110 billion of damage. Every year, millions of people are affected by extreme weather or geological events that turn into disasters. Geohazard like earthquake took more than half, 58% of all the lives lost to natural disasters between 2000 and 2019. This month, there were 2 tragic disasters, namely an earthquake in Morocco and floods in Libya, which took tremendous human lives. We need to take any action possible to avoid any unnecessary fatalities. Operating at the interface between natural and social sciences, education, culture, and communication, UNESCO is enhancing preparedness and building resilience at local, national, and regional level. For instance, UNESCO is training maçons in Haiti how to build homes that will be more resistant in an earthquake. UNESCO is also putting early warning systems in place around the world for tsunamis, flooding, and drought. We are working with local scientists and communities to restore mangroves, as these ecosystems are the first line of defense for coastal communities confronted with climate change. Since mangroves forests can reduce the strength of waves and winds and protect against coastal erosion. IPRED is playing an instrumental part in UNESCO's work to make the built environment more resilient. IPRED was established in 2008 with the support of Japan. Excellent institutions from 11 earth-prone countries are participating in IPRED. For the past 15 years, IPRED has developed technical guidelines, conducted post-earthquake field investigations, and provided earthquake-prone countries with technical advice and policy advice on how to build to last. I would like to thank the members of IPRED for their active engagement. There have been so many devastating earthquakes around the world over the past 15 years. We need to take a comprehensive approach to making the built environment more resilient to geohazards. For example, seismology is crucial to understanding the geological phenomena of when and where an earthquake could occur. Engineering is vital to understand the way in which buildings behave during an earthquake and how to strengthen them. Scientific knowledge needs to be translated into policy. For instance, policymakers need to adopt building codes and building control systems in order to make sure that engineers are attuned to scientific knowledge. This comprehensive approach should include all sectors, from the engineers who design the buildings to the municipalities who check the buildings plan to ensure that the legal codes are being followed. This comprehensive approach should extend to the private sector and to individuals who need to be made aware of the risks they face and invest accordingly. Nor can the quality of the masonry be overlooked. IPRED has been discussing this broad aspect. Today, we shall be hearing about different lessons learned around the world on how to reduce earthquake disasters. In closing, I wish to thank all the participants for committing to disaster reduction and looking forward to continuing our work to ensure that more resilient buildings become a global reality. Thank you.
Ambassador of Japan to Ankara, Mr. Takahika Katsumata will participate also with his video message.
Dear friend of UNICEF, distinguished participants and guests, this is Katsumata Takahiko, Ambassador of Japan to the Republic of Turkey. I'd like to congratulate you all on the opening of UNESCO-Ipred International Conference. Taking this opportunity, I'd like to also express once again my heartfelt condolences to the victims of the devastating earthquakes in Turkey. Japan and Turkey have cooperated with each other for many years as earthquake-prone countries. After the earthquakes occurred on February 6th, the government of Japan immediately dispatched the Japan Disaster Relief Team and conducted the rescue operations in Kahramanmaraş province. In early March, the Japanese government also dispatched a team of experts in seismic isolation and earthquake-resistant technology, which is also the theme of this conference, to help the recovery and reconstruction of the affected area. In addition, Japan implements a grant aid project for the safe disposal of earthquake debris and recycling of rubbles, and the technical cooperation based on Japan's experience and expertise, such as supporting the reconstruction plan of Kahramanmaraş and introducing earthquake reinforcement technologies. Furthermore, the Japanese government has been preparing to provide new concessional loans to further support the recovery and reconstruction of earthquake-stricken areas. Academic research teams, including the Architectural Institute of Japan, headed by Professor Kusunoki, who is scheduled to participate in this conference, as well as Japanese companies, are also providing various reconstruction supports. In this way, industry, academia, and government as all Japan are providing support in their respective fields, hoping for the early recovery from the damage of the earthquakes. Finally, I'd like to introduce the Turkish Japanese Science and Technology University to be inaugurated next year, which marks the 100th anniversary of the establishment of diplomatic relations between Japan and Turkey. This university aims to carry out world-class scientific studies, and it will start its activities next year as a graduate school in two fields in advance: energy and environment, and earthquake science and disaster management. Director Professor Yılmaz is also present at today's conference, and he will say a few words. We would appreciate it if you could get to know him and link to collaboration between universities. I'd like to conclude my remarks with wishes for the fruitful outcomes of the conference and hope that research in the field of earthquake disaster prevention for buildings and housings will progress, and that as many lives as possible will be saved under the spirit that no one should be left behind. Thank you very much.
I would like to invite Rector of Turkish-Japanese Science and Technology University, Professor Dr. Bekir Sami Yılmaz, for his opening speech.
Good morning, everybody. I'm so happy to be in Istanbul Teknik Üniversitesi at the moment, and I'm so pleased that the UNESCO and some universities organizing such event, the conference. That's it, IPED conference in Istanbul. So, having said this, I also thank to conference organizers and the vice president or vice rector of the university. I'm so happy that I'll have a chance to talk to you today with this occasion. Naturally, the natural disasters are the important events or the things that we have taken the lessons. And from that, we also teaches the lessons for the next generation to come in the light of science and technology. So there are so many things that we learn, but so many things that we need to teach for the next coming generation. For those who can perhaps safely design and build the cities and the environment and plan the things that would have an impact on the next coming generation. Although I'm not in the area of earthquake science and the management or disaster management, yet I'd like to say a couple of words more of it. We believe that the earthquake is one of the natural disasters that we have to learn from it. And therefore, my university, Turkish Japanese Science and Technology University, one of the programs, we give the priority to study what is the ways and the means of science that can be utilized to learn or to prevent perhaps the disaster after the earthquakes, or the early detection of the earthquakes if possible. Having said this, let me introduce Turkish Japanese Science and Technology University. But we need to learn things from the nature. Definitely, the human intervention to the nature will cause disasters. Now this century is the century that we need to learn the lessons and to minimize perhaps the damages which we cause around us, around the world. So I also mentioned, before we going into the TTU, Turkish Japanese University of Science and Technology, to share the sadness of those who survived from the earthquakes from Kahramanmaraş earthquake. And for those who lost their lives, warmly perhaps appreciate or send my condolences for those who remain, or relatives of those. So, having said this, I'd like to mention that the Turkish Japanese Science and Technology University was established by lateral ranking in 2016, and it became a reality in 2017 by law. And then the corona came. Naturally, there was a little bit of a break. 2021, I became a rector in November to this university. Naturally, I had a duty outside, and I joined the university in 15th of January 2022. Then we'll be working on because it is, I believe, a little bit of fortunate that we're not under the umbrella of Turkish higher education system. So therefore we have to write down our rules and regulations to make it more international school. So to do this, our mission is that we like to be one of the world-leading university in science and technology area, particularly in science. This will allow us to excel, in fact, to become one of the world, or one of the universities that can be recognized by the world. So our programs, as mentioned by the ambassador, we started with the energy and environment, and the following is the earthquake science and disaster management. So the cooperation is always open with you. So the model what we were selecting is like the MIT, Stanford, and Caltech, one of those universities. So our rules, regulations, as well as the principles that we are going to be adopting is to this. Of course, there are lessons to learn from Japanese universities. There are lessons to learn from the other universities, the university from Turkey, all over the world. We are always open for your suggestion, and you're always welcome to interact with us. Today, again, I'm congratulating for those who is participating in this conference and contributing to the development of understanding, definitely, of the earthquake and some suggestion for the disaster management, how we can do better for future. So I should thank you all one more time giving me a platform to talk to you here, and hopefully we'll be communicating with you more in the future. Thank you.
Thank you, Professor Yılbaş. And finally, I would kindly like to invite Vice Rector of Istanbul Teknik Üniversitesi, Professor Dr. Lütfiye Bırakata, for her opening speech.
Thank you very much. Dear rectors, dear distinguished guests, first of all, I would like to welcome you all to Istanbul Technical University. Istanbul Technical University is the oldest technical university in Turkey. And this year, besides Turkey celebrating its 100th anniversary, Istanbul Technical University we are celebrating its 250th anniversary. ITU also has had very close relations and joint research activities in the fields of earthquake engineering with Japan and many other countries in the world. The Structural and Earthquake Engineering Laboratory of Istanbul Technical University, which is one of the organizers of this event, is also celebrating its 30th anniversary. The laboratory was established after another major earthquake in Turkey, namely the 1992 Erzincan earthquake. These are very unfortunate disasters for us, but thanks to the Japan International Cooperation Agency JICA project, this laboratory continues its progress since then. Many distinguished researchers have been graduated from the laboratory during these 30 years. Many international and national research projects have been accomplished, and the results have been shared as theses, articles, reports, and seismic code items. As Istanbul Technical University, we are proud of being one of the few founders of the international platform for reducing earthquake disaster, IPRED, which brings together experts from many earthquake-prone countries like Japan. And in their annual meetings, IPRED members share and discuss their technical findings and experiences in the field and the consequences of catastrophic earthquakes like the one we had experienced on February 6, 2023. I'd like to thank all of you for visiting our country and university for the IPRED annual meeting and the international conference dedicated to the 6th February Kahramanmaraş earthquakes. I hope that the IPRED annual meeting and the conference will be fruitful for all member countries, and that what we have learned will be used to reduce the earthquake risk in our countries. I greet you all with my most sincere feelings. Thank you very much.
Thank you, Professor Ata. Now we will start our sessions. For our first session, Professor Dr. Faruk Özdağ as chairman, I would like to invite you. And okay, thank you. Our first session starts with the presentation of Professor Dr. Tuncay Termez from Istanbul Technical University, and the title of his presentation is A Giant Jigsaw Puzzle Mobilized by the 2023 Kahramanmaraş Turkey Earthquake Doublet, Cascading Multi-Segmented Ruptures on the East Anatolian and the Sturlu Çardak Faults.
Good morning, günaydın, konnichiwa. It's nice to be here. I would like to start first thanking Professor Can Yüksel for inviting me to participate in this international gathering. Welcome all to the rectors, our fellow colleagues, beloved students, and members of public and media. I will speedily present our earthquake source studies just after the earthquake so far was in Ukraine, and the great support of the United Nations in New York and also in Vienna, and now here in Turkey. So I named it the giant jigsaw puzzle, and that's a structure of the whole plate of motion in the region, and demobilized what we call Nurdağ-Pazarcık earthquake doublet threatening the northwest Syria. And it is a cascading, multi-segmented ruptures on this part of the plate boundaries. And it's the enormous importance of such an earthquake that we see mostly in Tibet, China, Japan, Chile, Alaska, in Saharan zones. So I participated willingly in organizing and by invitation of the distinguished fellows through United Nations support, although it's been targeted the earthquake engineering aspects more, but we need to know the reasons behind, like our director just said, and also the message from UNESCO. We need to understand the natural philosophy phenomenon behind. So if you believe the Japanese dynasty, they blame the giant catfish in Amazon for creating the big earthquakes. Or if you are believing to Greek mythology, they are blaming big gods hidden underneath the Aegean Trench, namely the Crete Island, and then a trench called giant Agelados. We use Aegean meaning. It's responsible for creating earthquakes. So this is a question of, in other words, literature and how many questions, rupture or not rupture, when, how and which mechanism, and what to do next. It's the biggest challenging questions. Thanks to the international efforts from NASA, European Space Agency, and so on, with the near-Earth space geodesy, we can get removed very fine-tuned data set to mark crustal strain or deformation like the seams, and not only a distribution of earthquake seismicity along the plate boundary, on ground measurements, or from the near-Earth urban satellite data sets, we can define the fast and slow velocities of any plate boundary ones. So this is a multinational, in fact, fast and furious, internationally collaborative, competitive study, racing against time to solve, to understand the reasons behind, and give the crucial information to the central and local governors and mayors to have organize search and rescue operations in the first 72 hours versus what a week ago. From the space geodesy, well, although in the other one we have smaller rates, but collection of about 40 years of near-Earth orbit satellite data sets, we are now able to give exact or average rates of deformation. We coded here, and in fact, it's in Aegean, for instance, the highest rate about 35 millimeters per year. With today's technology and data sets, included that exactly what I predicted and modeled and calculated during my PhD in Cambridge in 1990. That was again 35 millimeters per year. For 40 years of remote sensing data set, near-Earth satellite geodesy data set, proves earthquake source studies. So I got that number pure study earthquake source mechanism for the slip vectors. But I'll give you brief information. This is one chapter from my PhD thesis. I published in 1991 in Oxford. And all of a sudden we had an earthquake in 24th of January 2020 in Guangzhou, around its region 1.6.7. So I revisited this earthquake and published a paper in 2021. So about 30 years later, coming back to the similar conclusions. All of a sudden we were discussing about the reasons and why and how we tackle the problems. We had 3 earthquakes in a series. Nurdağ-Pazarcık, 6th of February, magnitude 7.9. 9 hours later, Şubat called 7.7, and then almost 2 weeks later, and in the Hatay-Samandağ region, another 6.1. So what's happening? So this is a challenging question. Within 12 hours, we witnessed, and then I decided to organize What's happening? Okay, so I organize meetings and uphold international cooperation through my contacts to the United States, Japan, China, and so on. And those color-coded, the rectangular boxes are the historical earthquakes where it's been heat and mapped from the Mineral Research Institute in Ankara, MTA, from the active fault maps data set. And if you analyze that, you see like in Hawaiian there was a seismic gap filled in 20th of January 2020, and then there are others in England, Barton, Karloa, still to rupture, like Malatya fault is sleeping, and the other ones. And this yellow one is showing today's subject, 6th of February, earthquakes epicenter. And as you see, there are historical data sets that need to be discussed, and I don't have time to go through all those. Well, anyhow, so this was a strike slip, as expected, left lateral strike slip motion, and well established with the aftershock activity, and a number of major aftershocks observed and threatened, and there will be severe damage in the region, and also that raised interest. Coming back to the today's tectonic model, every single piece of little black line you see is an active fault is capable of producing earthquake about 6.5. So then that was the publication in 2021, we done with our colleagues, and I organized this international fault. So to come to today's point, so this is the jigsaw puzzle, giant tectonic mosaic, and everything you see the thick blue lines, in fact the one that broken during this 6 February earthquakes, clear ruptures on the surface from satellite data, from earthquake seismology, seismotechnology, geodynamic modeling, even the tomography, also geotechnical studies in the fields, and I will try to address all those quickly. So what we do, if in case of earthquakes, we have a regional or global network of seismographs or seismometers to record register earthquakes. We have regional ones. Within that regional one, we have local network or even temporary reference or the emergency, of course, after an earthquake. So what we are doing is we are trying to increase the resolution of the results and the calculations. So today's subject is in the Kahramanmaraş area. Everything is pale color. It is unaffected by earthquakes. So what we have here, AFAD's strong motion stations and Turkish General Mapping Command, high-rate GNSS GPS stations, plus we have a near-Earth satellites monitoring. So every day, 2 days or 3 days, we are racing against them. This was just 24 hours afterwards to try to collaborate, accumulate all the data sets. So we did so, and this was 15 seconds of snapshots from our ongoing research. We were still trying to understand the super shear rupture in a small segment that triggered bilateral motion along the eastern fault zone, also Charlotte fault, and also triggered the other nearby smaller ones, and how we waited 9 hours. In case of 1992 Gölcük earthquakes in Izmit, we waited 3 months later. We had the largest aftershock, 1972 in Unesco. Likewise, in Erzincan, 1992, we waited 2 days, 13th of March and 15th of March. So these are the questions. And this is a multidisciplinary approach, multidisciplinary science, collaborative, fast freeze, and competitive studies against time, against the groups in the globe. So, since February the 6th, I've been collaborating with these institutions, and they are either opening their supercomputers to me, or they are sharing their data from NASA, ESA, in Japan, and Chinese institutions, or inviting me to deliver my calls to the rest of the world. First, we organized a fascinating IT year, and the European Material Seismological Commission, the European Union, Turkish Academy of Science, and I got small support from National Science Foundation in the United States, TÜBİTAK, and we had made a series of publications in 2 weeks after the earthquake in Seismological Society of America, and with the help of VSGS, of course, and Seismica. Then our competitive efforts were recognized by the United Nations, And I was invited to the United Nations General Assembly and Annual Science and Technology meeting in Vienna, and I presented this talk here, then followed by American Geophysical Union intervention to, or welcoming to our outputs, scientific ones. Then, of course, there was a huge group competing against US, Chinese Academy of Science, not to mention the Russian Academy of Science, of course, our good old friends from the University of Tsukuba and ICE, Geological Survey of Japan, and then we have been collaborating internationally, competitively, against 5 big publications in these journals. Science Action Days even have just published a paper in Nature Communications, and we have a paper waiting for proof in Nature Geoscience in a few days, and we have an increasingly accepted paper in Science, and there are others pending. So this was a snapshot, our first 2 months of results that I presented here in the Vienna, in the Hofburg Palace, on behalf of course, myself, but representing Istanbul Teknik Üniversitesi, maybe the Republic of Turkey. And this was well received, over 4,000 participants, and there was a severe condolences. Well, first, within the second day, in fact, I was woken up by a journalist from Australia in the middle of the night. Hey, wake up, there's an earthquake in Turkey, before our Turkish journalists. So then I collected first a few stations from Turkish GPS network and looked for the vectors. I said, this is serious. And then I quickly used computers in the University of Washington, Oregon, and ITÜ and so on, produced this map and released on the 8th of February in the afternoon to the rest of the world, and trying to attract attention why we have the historical earthquakes and the rates of the formation from 18 millimeter, 10 millimeter, to 5 millimeter to the Ananos Samandağ segment, even to the Türkoğlu, to the south, about 2 millimeter per inch. These are huge rates as far as earthquakes for seismology is concerned. So we waited, then this was 2 days of aftershocks from Papa, dead lots, and then we decided to wait about 10 days. Here, in fact, there's 11 days of aftershocks. We have relocated the advanced techniques like hyper-DB, hyper-inverse, try to identify precise locations of those on the surface of the map on 2D to 3D, and try to see where and how and what is going on and why we have some locations, seismic depths or bilateral or unilateral the distribution. And this was the first paper we published in Seismica. And here we found, this is in fact a small tiny piece of fault segment in Nurda, Gaziantep to Pazarcık in Kahramanmaraş, ruptured at a speed of 3.2 km per second and triggered around Pazarcık bilaterally to either way, and then of course the Sürgü Çardak also. And this is the resulting seismic moments, calculated magnitude 7.8, 7.6, and these are the velocity rates. I'll show you in a minute, but we do have, there are geologists among us, up to 12 meters of displacement in total in lateral, and in some places we have a vertical in the normal floating component. Maybe you have already seen it. This is the published over the scientific journals, of course, LinkedIn and Twitter, and this is the rupture animation that we have observed within 10 days of data sets, and then 9 hours later we had bilateral. Well, maybe I can show you this one more time. So this entire length about 500 kilometers broken, and here is about 200 kilometers in some locations. Fresh ruptures are mapped from neotectonics, that's about field geologists. In fact, we are still waiting from Turkey and also international partners to publish their observation from neotectonics. As far as earthquake seismology, near Earth geodesy or seismic geodesy data sets, we have it. We all have all the possible data sets, but not the field data set. So within 10 seconds, up to 20 seconds, this second one, or up to Hatay area in Samandağ portion, because this first event lasted about 120 seconds. We could have easily forecasted with early warning networks. It's a pity we missed it within 10 seconds because we didn't have real-time monitoring on that segment of the fault plate, or interplate boundaries, and this is the weakness of this sad news. Then we had a race against time against institution in US, China, Japan, and Turkey, and I collaborated with all my knowledge and existing data sets. And whatever you see in USGS website and find it called is our results, in fact, with our group that we published in this paper, and we provided all the data sets openly available, Turkish, international data sets to everybody. You can have a raw data, interpreted data, and then published data sets. As you see here, we have a time table here, and the first 2 days in a day, we had more or less roughly data showing the rupture of simply segmented fault branches and how we modeled. Within 4 hours, we were quite sure what's happening. Within a day, we had first optical radar data sets coming every day, or 2 days. We had the other satellites that passing owls and sentimental values and so on, trying to make or finalize our fine-tuning source rupture mechanisms and dimensions and the seismic energy, and we want to give a warning like Helici, also USA. And this was done quickly and after 11 May. And we published this was nearly a month later because there was an embargo from the United States Geological Survey, Minister of Defense and Foreign Minister of the United States to release this data because we used in the paper instead of Turkey, and they had to ask the United Nations and other institutional boundaries what is the political name, right, official name of the United Turkey and so on. This delayed our publication nearly two weeks, and yet we managed to publish GS8 and Pager and so on, and the scientific paper. Of course, every day or a week passes, we have many data sets coming from near Earth satellite to monitor optical data sets like a damage in the Hatay airport or any other branches along the eastern fault zone was visible, and it was also confirmed from the remote data set that even going to the field. And yet the final calculation is about 7.9 for the main shock, and then 7.7 is the second aftershock, largest in the Çardak and the Şurdu fault zone. Then National Academy of Science invited our group, and we had a quick questions and lessons learned within 2 weeks, and some projects published in Russian. It's here called Priroda, that's a nature equivalent journal in Russia. And yet, of course, our colleagues in China, Chinese Academy of Science, invested a lot of financial support and also computer and data sets. And we've been able to get the 2:45 after the earthquake, within 2 hours of the major one, and then within less than an hour in the second one, we were able to use only telescientific data set and look at some strong ground motion data sets, give a simple mechanism geometry and publish in 3D Science Scientific Journal in Earthquakes. While studying this one, we recognized there are plenty of these triangles are strong motion stations. Most of them are not recording a huge amplitude, but those wide open circles are the ones that has shown large amplitudes with like pulse-like ground motion, and these are the major areas or locations that we witnessed damage to the human kind and resistance. So this was a lesson to learn for earthquake engineering purposes, and we published this one in the earthquake science. Then we realized that there is, after 2 weeks, huge amount of aftershocks occurred, and we decided to accumulate all of them that precisely located, not only using P wave but also S waves, SH waves, arrivals to make a clear image with these 3 or 6 segmented fault branches on top of what we have already found in USGS and others that we published on top. We managed to give some hints and reasons on why and which portion of the faults are moved, and this was also published. And that one. Then, of course, our colleagues in Japan are forcing me to come together, so we have used their advanced techniques and the high-power computer facilities in Tsukuba, and used our initial models. That was first paper that we published, and that's 3D representation of that one, and that shows distribution from the first 2 weeks of data sets, and we managed to model the source propagation and the mechanism and distribution of the axis along M plus along stress transfer. This was also published in a well-respected journal, American Geophysical Union, and this is the outcome of it. Small proportion triggered the main branches and the evolution of the source mechanisms in time and branches on top of the AFAD's relocated, after the big relocations. And we come up with about 80 seconds of first glance moment distribution up to 0.9 and to 0.6, and there is a fast velocities in some direction. I will try to show a small animation about what we've done. These are already published data that you can find in the scientific journals. This was the first 3 to 4 seconds. This is in fact super shear what the suspects occurred and then triggered all the smaller branches, and these are the geometries of the fault a few seconds intervals, and this is the chart and the pseudo faults. And these are of course the seismic stations that we use on the global network, and the fits of data set. This is a technique developed by Japanese scientists based in the Earthquake Research Institute at Tsukuba University, and that we have managed to model the evolution in time, how it's evolved, and after triggering the display fault. This is the main branch. This is the 9 hours later survey chart, but what we see how it's evolving and which direction its energy is released. This is also published, and this again, and this, that was the I hope this works. I don't know why it didn't work. There was an animation here showing that this was the perspective view exactly on the fault plane. This is the one on the net view. So this was also published then. So we have published already 4 papers, and then we decided, okay, let's test our results. And using advanced 3D morphology, looking at the dynamic motions of it. We again using the strong motion stations, testing our models like Magnetic, USGS, Light, and this one, and showing how in this display fault back propagating in the Kötürge anomalous segment towards the harmonic segment, how it's happening. This is for that we need a huge power, CPU power to do the model, and this was also, I'm glad that's accepted and published in a very nice journal in the American Geophysical Union data sets. Then every week passes, we have more and more data pouring from field and from the satellite data sets, from strong motion and from the telescopic station, and different approaches. And we, with the Chinese Academy of Sciences colleagues, we published this one online last week, 2 weeks ago, and we've done. Okay, maybe for most of you are not familiar with the situation. For the AFAD's earthquake strong ground motion station distribution is fine. But for the Turkish command of mapping, GPS or high-rate GPS or GNSS station are very sparse, far away from the earthquake fault zones. Only a few of them nearby, and some of them already knocked down by the earthquake, and it's not recording, and there's no electricity, no building, and so on. There's catastrophic damages in some of the buildings. Then we didn't get static, kinematic, or dynamic vectors of in situ on the high-rate GNSS data sets. Then what we did, we collected all the strong ground motion acceleration data sets, inverted for velocities, and then from there to the displacement, as if their strong motion instruments are acting like a GPS station, and that's the kinematic motion totals. And combine those teleseismic and local wave seismological data sets and model with these 2 earthquakes. And in fact, in some locations, we have high velocities, rupture velocities, and some voids, gaps, and indicated 0.9 and 0.7 magnitudes. And there are locations up to 12 meters here. 13 meters of displacement along the survey and chart faults. Even some of them mapped in the field by the Turkish geologists. And this was accepted, published in Nature Communications. As I said, so we are mixing multi-scale data set, multidisciplinary approaches, multi-tasks, or using multi sophisticated methods together. So we need to accumulate first, if you are using teleseismic stations, we need to get teleseismic near Earth satellite data set to make them comparable and also sometimes mix them up for the third dimension. So what we have done in this paper in Nature, this is, by the way, accepted since 1st of September. We are waiting for the proofs. I tell editors and some officials are there on their annual summer holidays, but we are still waiting for the proofs. It's been accepted for Nature Geoscience. And using these satellite data sets and mixing with the Chinese, there are more than thousands of stations, like HiNet or also in the United States, also in Japan, and for 3-component broadband, shortwave, internet, you name it, and they are all real time. And we accumulated all those and selected high quality ones, and just to see the rupture directivity, and where we have superimposition of the waveforms on top of each other to increase the magnitude of the strong motion and so on. There are some technical details, and compare them to the Alaskan network. There is also an MBS network. But for these two earthquakes, we've done this one, and this is being done this year. And we come up with the analogous data. Now we are able to model near Earth orbit satellite data with the teleseismic array seismology in 3D. And this was a welcome, nice paper. This is the geometry. We were able to calculate the maximum slip rate from earthquake seismology and from seismogeographic data without going to the field. Up to the depth of the seismogenic thickness, looking for the displacement in depth, on the surface, lateral, strike slip, or normal faulting component, even some locations with tiny bits of truss components as well. And this was published. And from the China network and from the Alaskan network, of course, you're looking from the either side of the data sets from the epicenter. Then you can look from the back projection of those elastic waves radiating from east to west, west to east, and look for the velocities. And these are animations for the Nurda-Pazar mechanism, and that's showing or confirming our previous publications so far. And this was welcomed and in press now. Well, then science never ends. There is more data that's coming. As I said, this is one chance in 100 years to catch. In fact, the biggest or largest earthquake in Anatolia was 1939 Erzincan earthquake. That was magnitude 8.3. This is 7.9. Maybe if we can force the waveforms a bit, it can be magnitude 8, the main shock, and the second one is 7.7. And we've done holistic studies, whatever you can think of it, in seismology, to calculate the constant deformation on the ground, not only using all the available slow motion station, high rate genesis, temporary arrays, even in the mayor's offices, and the snapshots of the minor earthquakes, triggering one after each other every half second, 10 seconds, 12 seconds, and so on. This was, in principle, accepted in science, and we are waiting for proof, but waiting for some minor corrections. In this paper, what we are looking at is super shear rupture. By the way, we've done everything from scratch, not relying on the AFAS catalogs, SGS, Candid Observatory, raw data. We didn't use P waves, we used S waves at times to locate the shear waves and come up with the velocities in sector, for instance, subshear or super shear, Erkenek or Pazarcık or amorphous segments, and look at the fits of the observed data set and so on. And this is a nice contribution to look for the dynamic or static stress distribution on a point where within 10 kilometers or even less subshear and supershear, and we have some location here we exceed the Mach wave, and then this is unpredictable. Of course, the story doesn't end there. The major aftershock, later we had 6.4. Around the Hatay and Tete Samandağ, there is a tilted landslides in some portions, created local tsunami as much as 40 centimeter water reverberation should be tackled, and my colleague, my student, Seda will deliver that one. But this was, again, what we published in 2012 with Seda's PhD And this is the reason we were warning earthquake in this kind of tsunami in the region to be paid attention also. But I'll stop here to thank you all for giving me an opportunity to speedily deliver what we've done so far. But the story doesn't end here. Of course, we do have ionospheric reverberations of these big earthquakes, again detectable with this near-Earth satellite that I can merge those observations to the earthquakes source seismology data. This is not only electromagnetic wave distribution, but the reverberations, and that's the paper I'm working on it right now. Thank you very much.
Thanks a lot for this excellent presentation, Professor Tuncay. And we have some time to ask questions to Professor Tybers. Is there any question? Is there any comment? Yeah, please go ahead, Mr. Mehmet. Just a second, Professor Mehmet, just a second.
Yes, indeed. There are plenty of faults not shown on the active tectonic map of MTA, meta-active terrified apparatus. And that's shown or not studied or not discovered. It's been discovered here, and there are portions that are not even activated, especially for symmetry or logic fault, nearby small segments. But there are some segments around Samanda, Hatay, Turkey, down to the Syrian-Lebanon border, some small branches. And there are, in fact, some active projects that I know running, and there are no motion on them. Maybe because of the soil infection and some other problems, but it's not recognizable. But I know there are groups in the Middle East Technical University and MTA and working on some of those. And some of those displacements are calculated remotely from seismology and from the geodetic data sets, being confirmed by some of those locations by the geologists, but some of them are missing because it's a huge geography. We took about 600 kilometers by 450 kilometers rectangle, and this is the area you have to speedily do the field work. I think it will take years for some of them to be discovered. Also, like seismology trench studies in some locations should be made, and because of the vegetation and also the industrial problems, for instance, I didn't see any single fault going through the Kahramanmaraş city center and moved. These are the long distance. Maybe the question should be, if you consider the east autonomous fault like your finger is being geometrically banded. Every banding point, like a pivot or aspect of barrier, in fact stopped. The super shear rupture, it was a straight fault line, like one of the fault all the way from Erzincan to Kocaeli, we would have awaited more damage and disaster. In fact, for a magnitude 6.9, 50,000 dead is nothing. I was expecting something over 150,000. And then I compared to China or US or Chile or Alaska and so on. So this was an easy escape, but unfortunate one. But we could have saved those lives. Within 10 seconds, we could warn the early warning. This instrumentation is there in US, in Japan, in China, and maybe some Turkey. And we are not well trained as far as human or societal problems are concerned to secure the remaining cultures in the region. So we have Istanbul Teknik Üniversitesi well-educated scholars, worldwide standards in earthquake engineering or sciences, but we wouldn't maybe lecture enough to teach or reach some of those local or central politicians yet in time.
Yes, we have a couple of more minutes, but please could you speak louder, Professor Mehmet Çelebi?
Is the microphone open?
Yeah, okay. Last week I was in Ankara, and in Ankara by chance
Yes. It's a good old friend of mine. Well, I heard shortly. Very short answer. I'm aware of this project, but I think they are collaborating with Twitter or Rafado or Kandili, but I'm not sure about it. But in 1509 earthquakes anniversary, it was 2009, 500 years anniversary, I organized international meeting in Istanbul Teknik Üniversitesi in this very auditorium, and also in Kashmishla. I invited Roger Wilhelm as a keynote speaker with the others from MIT, and I persuaded him to install tilt meters in these suspected fault places, and he managed to install one of them, and it's, I think, 6 months of data available prior to this earthquake. About 4 millimeters per year is seismic deformations occurring, and it's open to us, and I will be able to use those data sets. But maybe I have forgotten to say at the end, I've been invited to many collaborative studies, but I don't have enough infrastructures in our department. But I have submitted a paper to US NSF, a research proposal with Californian seismologists, and another huge project to Chinese Academy of Science with a bilateral agreement. So Chinese and Americans are racing against in time with each other on this earthquake. So I've been trapped, caught in between. So I'm trying to be fair to everybody. Strict confidentiality, I collaborate with all of them. Thank you.
I would like to thank you very much, Professor Tuncay. It's my pleasure to invite Professor Seda Yolsal Çelikbilen from İstanbul Teknik Üniversitesi. She is going to present the article titled as Rupture Kinematics of the February 2023 earthquake at the Triple Junction, where East Anatolian and Dead Sea faults and Cyprus are converged. She has 20 minutes.
Good morning, everyone. Thank you very much for your invitation to this conference to present our results on the 2023 Kahramanmaraş earthquake sequence. After Professor Kayman's talk, I will continue to present our results mainly on the rupture kinematics of the 20 February 2023 magnitude 6.4 Hatay, Turkey earthquake at the Triple Junction, where East Anatolia and Dead Sea faults and Cyprus are common.
Get closer to the mic, please.
Okay. The contents of my presentation starts with the definition of the tectonic boundaries and main structures in the Eastern Mediterranean region, which is the most important one for our case is the East Anatolian fault zone, where these earthquake sequences occur. And I will show some tsunamigenic zones in the Eastern Mediterranean region, and I will also present the tsunami simulation results of historical 1822 7.5 Turkey, Syria historical earthquake and tsunami. The results of, after showing the results of my presentation, I will continue with the discussion and conclusion. Active boundaries and main structures in the Eastern Mediterranean region is represented in this slide. As you see, the active tectonics is dominated by the northward movement of African and Arabian plates with respect to Anatolia. In the east, we observe a collision between the Arabian and Anatolian plates, and in the west, the dominant motion is the subduction of African plate beneath the continental Aegean block. So these motions, because of these motions, Anatolian plate moves westward direction towards the Hellenic subduction zone. These tectonic movements produce main tectonic structures in the region. They are North Anatolian Fault, East Anatolian Fault Zone, Hellenic and Cyprus Arc, and Dead Sea Fault Zone. Here you see geodetic measurement results. The geodetic measurements indicate these plate motions, and as Professor Parmas said, the GPS velocities increase along the Hellenic subduction zone up to 35 mm per year. We observe 9 or 10 mm per year GPS velocities along the East Anatolian fault zone. When we look at the seismic activity distribution, we observe that the most of the earthquakes are concentrated along the Hellenic subduction zone in the west. But we can clearly define the other major structures by using the earthquake distributions. The East Anatolian fault zone, where the 2023 Southeast Turkey earthquakes occur, is a left lateral strike slip fault zone, and it extends between Karlova in northeast and Antakya, where links to Dead Sea fault zone and Cyprus Arc around the Amik Basin in the southern Turkey. Along its strike, it has several segments, and because of these earthquakes, some of these segments ruptured by causing severe destruction in several cities around the epicenters. These are the major segments: Karlova, Ilıca segment, Palu segment, Kütürge segment, Pazarcık Erkenek segment, Türkoğlu segment, and Sürgü Çardak Savrun, and also Antakya Amanos segments are the major ones. In February 2023, as we know, there are intense earthquake activity ruptured the Pazarcık Erkenek segment and Sürgü Çardak segment, and also Amanos segment with catastrophic earthquakes which have moment magnitudes of 7.8, 7.6 and 6.4. We can follow these segments, ruptured segments, by using the aftershock locations, as you see in the west, in the right. These earthquakes were followed by very intense aftershock sequences. By examining these aftershock sequences, we try to understand the rupture evolution and seismogenic depth, seismogenic zones in this area. The earthquake focal mechanisms provide us very valuable information about these rupture characteristics, and in general, we can see that along the East Anatolian fault zone, the earthquakes mainly occur with left lateral strike slip faulting mechanism, but it has significant amount of deep slip components. Some of them has normal component and some of them has a thrust component. When we go to the southwest, along the Amanos and Antakya Samandağ segment, we observe the deep slip component increase, and it caused transtensional deformation near the Amik Basin. Also, historical documents and catalogs reported many significant tsunamigenic earthquakes around Hatay-Antakya area, with earthquakes with intensity values of 10, 9 or 10, and they produce significant tsunami waves along the coastal plains of Eastern Mediterranean Sea region. In this picture, the stars indicate tsunamigenic earthquakes that are reported by with Borniko Mastri 2005 and Shbeyhan et al. 2005.
By using earthquake distribution and historical catalogs, we classified these zones as a tsunamigenic zones, 11 tsunamigenic zones. The first one is Amasra part of Amasra Shelf at Southwest Black Sea, Marmara region, North Aegean Trough, Gulf of Corinth, Western Hellenic Arc, south of Crete, Eastern Hellenic Arc, Cyclades, Seferihisar Kuşadası, southwest of Cyprus Arc, and Dead Sea Fault Zone and Levantine Basin. These zones are capable of producing tsunamigenic earthquakes. In my PhD thesis, we simulated these tsunamis, earthquake-originated tsunamis, by using our seismological observations. We simulated 7 historical earthquakes, as you see here. These spheres indicate the earthquakes, tsunamigenic earthquakes, and their assumed source mechanism parameters. Today I will show our results of these simulations from 1822 Hatay, Syria tsunamigenic earthquake. What is tsunami? Tsunami is a series of ocean waves generated in the sea bottom by an impulsive disturbance that displaces the water. They are shallow water waves and they will affect from the bathymetry very much. So we have to know the bathymetry accurately. In our simulations, we use this bathymetry data. It indicates in Eastern Mediterranean sea bottom there are different tectonic structures which affect tsunami wave propagation, such as Herodotus Basin, Eratosthenes Sea Mountain, Anaximander Mountains, etc. Also, the tsunami waves propagate to the coastal plains with the velocity related with the water depth and the gravitational constant. This is our results of 1822 7.5 historical earthquake. As you see here, we assume a fault plane, which is shown with shaded rectangle, and we assumed a source mechanism parameters for this earthquake. According to our simulation results, we observed up to 3 meter high tsunami waves in the Iskenderun Gulf, Adana, Mersin, and Cyprus. Eastern part of Cyprus and Levantine Basin. So this region has a potential to produce tsunami, and in this presentation I will show what is the reason of not producing tsunami for 2023 Antakya earthquake. Here you see after the 6th February 7.8, 7.6 earthquakes, we observe some sea level rises up to 15 or 20 centimeters in Iskenderun, Arsus, Mersin, Erdemli, Gazi Mausa, and Girne in Cyprus. In a recently published paper, Hu et al. 2023 reported that this sea level rise is related with the landslide origin. Tsunamis occurred because of these Kahramanmaraş earthquakes. In our studies, we model the teleseismic distance seismological data to obtain the fault geometry of the earthquakes. And also we can determine source time function, which show us the rupture evolution during the time, and also the focal depth and seismic moment. After obtaining the faulting geometry, we can try to understand the slip distribution on this fault plane. We divided the fault plane into several subfaults, and we model again teleseismic distance, P data, P velocity, P displacement, and P velocity data to obtain the faulting area, fault length, fault width, source time function, amount of displacement, stress drop values, and slip distribution on the fault plane. When we look at our results, we located 777 earthquakes, magnitudes range between 2.5 and 6.4, occurred in 3-month period.
they mostly occur along the Amanos, Samandağ, Antakya fault segments in the south of the Kahramanmaraş. And these earthquakes clearly indicate very shallow depths, up to 10 or 20 kilometers of the crust. They indicate shallow seismogenic depth in this region. By also analyzing the vertical cross sections, vertical distribution of these earthquakes, we can understand these earthquakes or these faults deep to the west or northwest direction, as you see from EE prime and BB prime section. When we go to the north, towards the East Anatolian fault zone, the earthquakes mostly occurred strike slip fault mechanism. So we can say that in Antakya, Hatay area, the deep slip component is significant, but when we go to the north, the strike slip component, it will be dominant. Why this is important? Because for tsunami producing, for tsunami occurrences, deep slip component is very important for disturbing the area, for displacing the water. Our immersion results, as you see here, we model 31 long-period P waves and 14 long-period SH waves. The solid black lines are the observed waveforms, the red lines are our synthetic waveforms. By using the best fit, by obtaining the best fit between observed and synthetic ones, we can define the source mechanism parameters of the earthquakes. According to our results, 20 February 2023 Hatay earthquake occurred with oblique left lateral strike slip faulting mechanism with significant deep slip component. The focal depth is obtained as 12 km and the source line function indicates very simple rupture on the fault plane. Also, we check the regional distance stations to understand the source geometry, and this immersion here we use the regional distance stations shown with blue triangles, and it shows similarly an oblique left lateral strike slip faulting mechanism for this earthquake. To understand, or alternatively to estimate moment magnitude of this earthquake, again we use regional distance stations and we calculated source displacement spectra. We try to fit our synthetic source displacement spectra with the observed ones, and it yielded a coda-derived moment magnitude of 6.2 for this earthquake. After obtaining the faulting geometry, we tried to understand the slip distribution and rupture propagation on the fault plane, and we divided the fault plane as 18 along strike subfaults and 10 along deep subfaults. In this immersion, we observed that the most of the slip is concentrated along near the hypocenter, or northeast part of the hypocenter, with a maximum displacement of 60 cm. Here you see the teleseismic P displacement waveforms. Fits are shown on the right of this slide. By using the seismic moment and the size of the faulting area, we also calculate stress drop during this earthquake, and it shows us this earthquake is an interplate earthquake with a small stress drop values. Also, we checked the joint immersion result. We modeled the teleseismic broadband T displacement waveforms along with the strong motion data. The strong motion data give us the details of the rupture evolution, so they are important for us. And the immersion results similarly indicates us very simple rupture, concentrated at the hypocenter, and the maximum displacement is about 1 meter for this case. So
Professor, could you wrap up your presentation in a couple of minutes, please?
Okay. So we can say that a northeast-southwest directed rupture propagation and the coseismic horizontal displacements, mainly along the strike of the plane and slip distribution concentrated at the shallow part of the fault plane. The GNSS data also confirms the left lateral strike slip kinematics of the rupture with these amount of horizontal seismic displacements. As a discussion, we can say that in Antakya, Hatay area, the dominant motion is left lateral strike slip, but the deep slip component is significant with extensional deformation. Our slip models similarly indicate very simple rupture and unilateral rupture propagation, a single circular shape asperity with amount of 60 cm or 1 meter around the hypocenter and small static stress drops. We suggest that the fault length of about 25 km was not sufficient to reach the Mediterranean Sea, that with notable amount of displacement that is capable of triggering tsunami, and hence this earthquake could not produce tsunami waves in the eastern Mediterranean basin. But in future, if there is a large earthquake in this area with a moment magnitude larger than 7.5, this will be a probable source for tsunami wave occurrences, mostly in Iskenderun Gulf, Adana, Mersin, and Levantine Sea basins. So, seismological observations and information will provide us very valuable data for understanding these conclusions. This study is financially supported by İstanbul Teknik Üniversitesi, Turkish Academy of Sciences, the Scientific and Technological Research Council of Turkey, and Science Academy of Turkey. And also, I would like to thank you to our colleagues from İstanbul Teknik Üniversitesi, Kocaeli University, and Yıldız Technical University. Thank you for your attention.
We have a couple of minutes to answer several questions and comments. Take the microphone, please.
Thank you very much for your time. I have a general question actually to be from highlights as well. Is there anyone or any group doing detailed mapping of the fault fractures of the first and the second event? It's a big challenge. The first one is about 300 kilometers, so it's about 60% of the entire fault line, and the second one is 150 kilometers. So I just wonder whether there is a detailed map of the fault fractures, like perhaps LiDAR mapping combined with the fault mapping very detailed, and also slip distribution of the fault fractures in the surface account. And I think the ultimate question for the practical purposes is to the structures, especially the houses and building collapse that is chance. So I'd like to know how much or what is the percentage of the houses and the buildings that collapse, not just because of the shaking, but because of the surface structures. And also I'd like to know also, is there anyone mapping the landslide and invasion? Because that's the ultimate question. How many percentage, how much the building and the houses are damaged, particularly collapse, due to ground formation, superstructures, and also landslide and invasion, not just shaking. Thank you.
Don't forget the mic, please. Get closer to the mic, please.
There are several groups in Turkey map the ruptures, surface ruptures after these earthquakes. In our studies, we modeled the teleseismic data to understand the rupture evolution. So we cannot observe a surface rupture for this
Antakya earthquake in our simulations. So the maximum and average displacement is so small for the case of Antakya earthquake. But for the 7.8 and 7.6 earthquakes, the ruptures are up to 8 and 10 meter horizontal displacements, as we know. I am not sure the collapsed building amounts. Maybe Professor Kahramanmaraş can answer these.
Okay. Is there any other question or comment? Professor
Thank you very much for asking very crucial questions. There are a number of groups from the universities organized by Science and Technology Council, at least all of these groups, doing this surface mapping, their own expertise field. We are not only using geotechnical structural geology point of view, but also using advanced remote sensing tools like LIDAR and so on, 2D and 3D. Yeah, okay, and also from the slow motion seismology records, from the seismological point of view, we can distinguish why there's a huge imperfection on some certain areas, why there's no signature in some locations, and huge collapse. And for that reason, we published already 3 papers from the point of view geophysics and seismology. And also for the construction or earthquake engineering point of view, I'm not an expert, but there are groups of our university members. They need to the field to nominate or analyze individual buildings from site to site, location to location. As I said, 600 kilometers wide, 450 kilometers rectangle, there is huge. Even the government, central government itself is not capable of giving right numbers after 6 months yet. And this will take time, maybe another 2 years, maybe 10 years now. And what there are some groups in MIT and Harvard and USGS that I know they are simulating, and the reason why there is a high rise or low rise business called total collapse by using the game tools like playing in a place station with artificial intelligence, the learning tools, and there has been beautiful MIT and PhD thesis just being Wyvern over the summer, and I know that there's a paper coming out on that very subject that's from computer-aided deep learning and cyberspace and related data sets. So the next 10 or 20 years, maybe 30 years, will pass and we will still be studying these earthquakes. Thank you very much.
Thanks a lot. Thank you very much once again. Now it's my pleasure to invite here Professor Anastasios Sekos from Bristol University to present his article, which is titled as The Hellenic Renaissance Mission after the February 6th Kahramanmaraş earthquake sequence in Turkey. Lessons learned and opportunities for international collaboration. The floor is yours.
Sayın katılımcılar, günaydın. Değerli için çok teşekkür ederim. It's my great pleasure and honor to be here among you today, and I would like to particularly thank Professor Zhang for his kind invitation. This paper is mainly to summarize the observations made by the Hellenic reconnaissance mission that visited the central area after the earthquake sequence. Obviously, when we say lessons learned, that's pretty much the lessons we learned, because apparently for these earthquakes we got more experience, more data, we can contextualize way better. But perhaps the benefit of this presentation is just to get an idea how things were perceived with the eyes of your neighbors that are facing very similar problems as good expert seismologists have highlighted previously. I also took the liberty, to be honest, to include a few slides paving the way for some discussion about what we can possibly do in our countries, because we keep on facing devastating events again and again, and this is obviously a very important international problem. So without further ado, I would like to move on with See, the local expertise is always better. So our mission actually took place in April, that is some months after the earthquake, because it took some time for us to prepare. But I'm going actually to present these results with the hat of the Greek Association for Earthquake Engineering, as well as of the National Technical University of Athens, which I hold a small dual appointment as well. So after extensive, very fruitful collaborations with the Turkish side and AFAD, a group of 17 people, all professors from NTUA and members of the academic board, visited the region. And this required quite some preparation, because obviously this is a place that you cannot just go without thinking very carefully what to do and when. But we had the pleasure to work closely with AFAD, particularly the director, Professor Tatar, and also Recep Zakir, who was extremely helpful, and we contributed as much as we could by essentially uploading data by using the mobile app that was available for the people on the ground to be able to essentially enrich the database of external observations from the international teams. We also used our own mobile app that we use as a Hellenic association when we're visiting post-earthquake regions in Greece, Albania, and worldwide. We also use that in Turkey to duplicate our, let's say, data. For your information, this is an open repository. You can just drop us an email and have access to all the photos and data that have been collected, that are classified by earthquake, distance, intensity measuring, and overlay, BSHA maps, the distribution of IM in space and the like. They are distributed by structural typology. Pretty good, I think, for essentially educational purposes or for empirical facilities in the future, and so on. So you're welcome to visit this or drop us an email, as I said. In terms of seismological background, apparently this was extremely well covered already, so I'm not going to shed any light, other than saying that for us, I mean, for people visiting from abroad, it was very important to try to know what we should know. In this case, apparently this is a very well-studied region with faults that were known. Essentially, the seismicity was on the surprise, and these things were kind of in the radar, very well mapped in the past, also reflected in the Turkish group. We also knew very well, by using USGS maps, that what we would see on the ground was essentially cumulative damage after many earthquakes. So we couldn't really associate it with a specific IM, yes. But it is the practicality of the problem, that it's never going to be a single earthquake. Christchurch, also the Italian earthquakes 2016, the Kefalonia earthquake, these are all dual earthquakes or triple earthquakes, events that accumulate damage on the structures. So whether we like it or not, that's part of what we need to design for somehow. And like I said, we knew that you knew that this is a high seismic region. We were very positively surprised by the breadth of data that were released so far by Turkey, AFAD in particular, because this has been extremely useful to contextualize and understand what we're about to face. And I think this is working very well. I think based on Greek experience, it would take some more days for data to be released, and definitely the accelerometric array in Turkey is way more dense, which is actually good news. Our schedule included all the areas that you can imagine, starting from Kahramanmaraş, and then going down to Islamiye, Skenderun, and Antakya, the Hatay region. That was about 500 kilometers in 4 days or so. Not a very extensive visit, but quite enough to understand a few things. So these are just photos that can enrich a little bit our thinking. Like I said, I'm not going to bring any new knowledge to you in particular, but there are some things that we expected to see and some others that we didn't expect that much to observe. So obviously building collapse, we knew from the news that would be a case. Pounding building to building, we've seen in the past in several quakes. Okay, this is something, some stories that we have observed. But in fairness, at least ourselves, we have never seen a case where so many adjacent buildings collapsed essentially on top of the nearby ones. And this is because, particularly in Greece, the magnitude of the earthquakes can hardly be above 7. So, because of the locations of the earthquakes that happened, let's say during the last century, there has never been such an extensive collapse of the building stock to affect the nearby buildings. But in this case, obviously, given the magnitude of the earthquake, buildings interacted way more substantially. There are also some characteristic photos that you can see that some columns have been entirely sheared off. This is actually a very redundant structure, if you like, because the beam is essentially overhanging successfully, so the building did not collapse. But like I said, this is not something that we observe every day. Several photos of these extensive images of shear walls essentially failing out of plane because of pounding, and also very extensive damage that you would only climb above rubbles to observe in Hatay and Antakya. Damages of historical, religious or cultural structures, masonry buildings, all that, let's say, the Mediterranean region in particular is particularly vulnerable. We've seen Morocco, we've seen Central Italy, like I said. This is construction types that are very common in this region. In terms of damage to infrastructure, I think, relatively speaking, please correct me if I'm wrong, but the response of school buildings, maybe perhaps they have been retrofitted in the past, was reasonably good, if I may say. But obviously there has been some very extensive geotechnical phenomena that we saw. Essentially, this triggers the thoughts that in the Mediterranean region, because of touristic purposes, with all this exposure essentially along the coast, it is very common for people to be building. That's not the case close to the coast, but I'm just referring to the risk that we face in soft soils in general. But clearly, the question that is raised in terms of liquefaction of building like in Skanderum by the coast is whether we allow construction in this region, how we impose by foundation and make sure that settlements and geotechnical damage is not going to be the case. In terms of interpretation, obviously, it's pretty clear, I think, what is the reason for this devastating result is essentially the intensity and the distribution of the intensity in space back-to-back with these two earthquakes. You can see the microseismic intensity that is overlapping in several regions, and then multiple earthquakes happening. Just for context, if you plot the spectra from the Turkish sequence of the Kahramanmaraş earthquake, and then you just plot the tiny little figure from the Athens earthquake. The Athens earthquake, because of exposure, that was 6.8 magnitude earthquake in 1999, caused 4% of the country's GDP. So, in terms of risk, even a way smaller earthquake had huge consequences, so there's no surprise about what we've seen. There is an issue of quality control, obviously not only in Turkey. If you go, let's say, in the suburbs of large cities in Greece and in other Mediterranean countries, there are buildings that have been built overnight without proper control. We have control to things that are done under the light. I'm not going to get into details, but just to distinguish between quality control of existing new buildings and buildings being substandard with smooth reinforcement and let's say quite scarce reinforcement because they have been built before the 80s, let us say. So these are two classes of buildings that essentially we cannot escape from. They are there. We either have to do something with that, which is not so straightforward as we're going to see later on, or it's very hard to retrospectively, let's say, cure. So these are just images to inspire about how could this be avoided and what we could do for buildings that have been built in the past. Smooth reinforcements, so immediately we understand that they are coming from a different period, they have been constructed with old codes. So to some extent we understand that their performance under such an intensity, after such a duration, for such a large number of motions, okay, we understand. From newer structures, yes, there is a discussion about how we could prevent it, and like I said, what we would do in the future to avoid reinforcement of this pattern, and lack of shear reinforcement, failures of this type, which is okay, good for textbooks, but apparently in real life shows that this random placement of reinforcement, which, like I said, is not just an issue in Turkey, it's in many places in the world. Also for your information, just to note that this flat slab system without beams is not used in Greece. It's not allowed. The performance of these systems is to be analyzed, and I'm sure you have more refined understanding, but we've seen a large number of these structural typologies, which in a sense was quite surprising given the background that we had for our own structural culture. This sometimes is combined with problematic reinforcement and open stirrups and smooth rebars and all the like, so the lack of beams perhaps is not helping that much. But on the other hand, success stories like seismic isolation, which seem to work very, very well in Turkey, particularly for hospitals that have been designed with this method. For context, in Greece, seismically isolated buildings are just three: the Acropolis Museum in Athens and two large cultural centers, Tharus and Anas Foundation cultural foundations. So there is no, let us say, it seems to be very expensive for the Greek construction companies to build with seismic isolation provisions, whereas in Turkey, I think you're paving the way for widespread, lower cost, locally produced use of bearings to protect the structure from damage. We've seen here cases of isolators that essentially locked, but the beam was broken and there was evidence that they worked very well, and there are hotels that were functional next day essentially. So overall, this is a message to convey, I think, to other parts of the world. Finally, also, I would say that the tunnel form that seems to be quite common in Turkey is not used. Actually, people didn't even know about that in other countries in the south. So this is something that seems to have worked very well. I'm sure that the speakers will say more about that. Seems to be pretty, let's say, quick. Maybe there is some issue about the modes and whether these are dominated in one direction or not, but perhaps this is something that is a solution for the future. And obviously code compliance. Where buildings collapse, simple buildings, regularly planned, regularly high, with appropriate shear walls, designed to the codes, good quality control, and they survive. Obviously this structure doesn't have all loads. Masses are a little bit reduced, but that's, I think, the message we should stick on. So I'm sure you know all about the loss of this devastating earthquake, and it's pointless to say more about this rather than helping all the people, thanking all the people who have helped us make this reconnaissance mission and collaborate with the Turkish authorities. For context, this is the second time that we have excellent collaboration, because following the 2020 earthquake, we worked very closely. Established a collaboration between the Hellenic Association for Earthquake Engineering and the two Turkish associations for earthquake engineering, and ERI produced a clear report with more than 170 authors. So I think the community, the scientific community between our countries is really working very, very well. Another two things that keep us awake, I'm sure they keep you awake as well in the night. This is, like I said previously, we acknowledge what the problem is, but the solution is not obvious at all. For example, in Greece, 70% of the buildings are substandard, have been designed before the earthquake of the 80s. Their seismic provisions are the ones introduced in 1959. That's 2/3 of the building stock. Now, following the Turkish earthquake, the Greek government immediately put forward a law for rapid visual inspection of schools and hospitals. That's 16,000 buildings. That will take a year on paper, I would say 2 years in Mediterranean times, maybe more, and then requires a second degree of inspection and a third one, and then funding for retrofit, somebody to 5 billion euros and retrofit the public infrastructure. And then what about the private ones? In Italy, they've got the seasonal bonuses, you know, they give some financial incentive by tax deduction. But the problem is, somebody needs to pay to upgrade. One problem. The second is that, like I said, when there's no quality control in new buildings, there is not much you can do later on, because if these people had the funds to build properly, they would have done so. So we're talking about low-income countries or low-income regions in developed countries, which is a huge problem. So now with my Bristol hat, if you like, I'd like to introduce you in the last 10 minutes that we've got how we tried, I don't say we've solved, but we just tried to contribute in addressing this problem in low-income countries. Essentially, investigating low-cost solutions with a program that we got funded by the UK Research Institute and supported by the World Bank, in collaboration with many international universities, to introduce these low-cost solutions in countries like Nepal, for instance. This is a large project. I'm just going to go straight directly to the experimental part, but just because we're talking about quality control, this is a trial and error way to identify whether bricks can be used or not in this context. So with that in mind, either we acknowledge that quality control is not guaranteed and we try to introduce some fuses in the system that won't rely on whether the reinforcement is corroded, as you see in this photo, or the buildings are not built by the codes, I don't think we can solve the problem. So we try to introduce a local seismic isolation at the base of the structure, which works in two ways. The structure is supposed to be built as normal by the codes, the Nepalese codes or the Indian codes in this case, and we introduce a fuse at the base of the structure. So if we exceed the friction force, the building is going to slide. Note that we accept that if it slides, utilities are going to break. So the performance objective is just collapse prevention. Okay. Lower income countries, lower performance objective expectations. And of course, in terms of existing solutions, you do not rely that you test realistic things in the UK. So you have to ask local workers, build with a local culture, and then test simple solutions with wireless, for instance, in the local context, in Kahramanmaraş in this case, and then repeat that many times and see how by introducing this wire mesh you can improve, let's say, the strength and ability of the system locally. And this seems to be working very well. Now, in terms of new structures to introduce this fuse, like I said, we started with a mixed sand rubber system, just to make sure that we can effectively apply an acceleration cap. You can see here the red line is the response, the blue is the input, so the system at some point it slides, and we repeated in small shear box tests the identification of the friction coefficient to understand how the system is working. So we did this test at the laboratory, the earthquake laboratory of the University of Bristol, the old one because that's the new one, but because we needed vertical acceleration, since we're talking about sliding, and friction, we did a test in the old lab, which means essentially a 6DOF system, as the one that you're seeing here, with a capacity of about 10 tons, 2G acceleration in both directions, 6DOF. And you can see here that the system at some point is going to slide, as you will notice, which is good news, but maybe you can see that it's also tilting, which essentially is not a very reliable way to solve the problem. So we didn't call that a success, to be honest. We thought that this is not a good idea. We ruled that out, and we introduced a more controlled interface for sliding between a sandwich composed by PVC, sand, and PVC. With that you can see here how we're laying the sand. You need to do some grain distribution studies to understand exactly what sand you're applying and so forth. But remember, that's just a fuse. So no matter if the friction coefficient is 0.2 or 0.22 or 0.18, it doesn't really matter because it's aligned with the design earthquake, and just in case the earthquake exceeds the design acceleration, the system, like you see in this experiment, is going to slide. So it worked in the lab. By working in the lab, you can see that you end up with some residual displacements, which is, I think, the red one here that you see. But definitely the accelerations are kept at the level that they are capped. And obviously the key thing here in my last set of slides is how to control this friction coefficient. So sand would give you around 0.2, 0.3 in some conditions, 0.18. Can we have it later? Yes, we can. If we introduce rollers, we could bring it down to 0.08. But do we really want a building to be sliding so frequently? No, perhaps. All I'm saying is that there are techniques to play with your level of sliding threshold. And then we had to do some numerical analysis to predict at least what would be the response of this system in case, probabilistically, in case of using several number of earthquakes. I'm not going to get into the details because I think I've got just a couple of minutes. All I'm saying is that if you compare, let's say, the conventional system on the left with seismically isolated, with this PVC sand PVC system, the system on the left collapses, the system on the right does not collapse. Obviously, this depends on many factors, so we have to approach that statistically, but you can see some snapshots of how the ductility demand is reduced between the conventional black line, which ductility demand, that's rotational demand, is 8 and is reduced down to 2. So we definitely, for very high earthquakes, we reduce the energy that is entering the structure. And if you compare all the black lines in this chart with all the red lines, black lines are conventional, red lines is letting the system slide. Always on the left, which you see the maximum building total drift, that is the degree of damage, is always reduced. How much depends on the ground motion, depends on the friction of the coefficient of friction, because if it's very low, then the system will slide before it gets damaged. If it's very high, it will probably get damaged before it starts sliding. So that's a design parameter actually. And then with the probabilistic assessments, how much is the maximum displacement, how much is the residual displacement. The residual is pretty much 2/3 of the max statistically, and we also observed, I think that was pretty obvious, that you can play with the behavior factor. Because if you use a very high behavior factor, as it is the code in the pole, for instance, this means you will reduce your strength a lot. By reducing your strength a lot, your structure will be damaged before sliding. But if you would like to combine ductility provisions for the superstructure and a moderate behavior factor and the sliding fuse, then the performance of the system is really very good. It doesn't depend that much on pulse or not pulse-like motions, on the direction of motion. I'm getting directly to my last slide in terms of results, which shows that for design acceleration, twice the design acceleration, 3 times the design acceleration, if you compare the first with the second slide, or the third with the fourth, always it is greener, always. By introducing sliding, the performance is way better. By keeping and not reducing too much the strength with a large behavior factor, the results are always better. That's, you can find our applications and you can refer in more detail. So final thing that we did was that we designed a real building in Kathmandu with this technique. That's the technology readiness level 7, let us say, which means pilot construction of the idea we had in the past. With the aid of the National Society for Earthquake Technology in Nepal, we designed the foundation, we did tests about uniform or non-uniform friction distribution along the slab, we designed the superstructure, we resourced different distributions of grain size and different types of sand from different rivers. Just for context, if it is harvested from the bottom of the river, then sand is washed out, rolls better, friction coefficient is lower, sliding starts faster and easier. So with that, we did some sensitivity studies on the water, pressure, dry, wet, and all that, angularity, whether they're going to roll, whether they're going to rock, whether they're going to slide, I mean, at the particle micromechanics level, and we ended up with the design of the system. You will see here, final slide, friction coefficient is a design parameter. You design for that, and actually you can control that. Behavior factor is the designer's approach. Ductility class, the Eurocode, is also a designer's approach. Performance objective, this one is not recentering. Now we've got a new grant where we're recentering the system with cables. But, okay, for this cost, you cannot meet all performance objectives. So some photos of the school as it has been built. You can see here how the sliding system looks like in actual construction. Maybe there is a video here that can show you a little bit better. Note that the parapet wall is sacrificial. There are 35 centimeters of gap. If you slide a lot at maximum displacement, this is going to be sheared off, but that can be rebuilt easily. There is no foundation in a conventional sense. There is obviously a mud foundation, but the structure is built on top of the ground to make sure that there is no pounding on the boundaries. So with these photos, and actually the final photo of how the building looks like right now, I would like to thank my collaborators and close with just 2 remarks. Inspired by the Kahramanmaraş earthquake and also with the work that people are doing around the world. At a wider scheme of things, I think the problem is not technical. The problem is financial. Technically, problem solved. Tactility solved, seismic isolation solved, other active control techniques exist. Who is going to convince the people who make the political decisions to invest now beyond for something that will show results beyond their political horizon? That's a very big argument and a very difficult thing to do. The second is that for low-income countries or low-income areas or areas that we don't trust quality control, it is not very realistic that to rely on technology to be widespread used to make sure that we resist seismic forces in the way we think we do, to meet very challenging performance objectives. Sometimes I think it is better to do a little bit, which is better than nothing, upgrade just a little bit, which is better than nothing, invest so much that we can do that at a large scale, just to prevent collapse with low-cost techniques. Otherwise, we were expected in all the regions that we don't have very good control in our countries, everything to be implemented as we've got in the code. I think it will take a lot of time for the building safety to converge. And this creates a huge safety gap between different communities of people, if you like, around the globe. As a closure,
yes.
Yes.
It is almost over. Please wrap up your talk.
My last sentence, actually. Okay, thank you for your patience. As a last sentence, I would like to say how pleased we are, let's say on the Greek side of the Aegean, that we have so wonderful collaboration with our colleagues in Turkey, and I think the problems that we share are common, and it will be very important to continue our collaboration in the future. Thank you.
I think we can devote a couple of minutes before we go break for questions. Is there any questions? Yes. Please don't hesitate to ask.
Hello. Very interesting presentation and very focused on the impact. The fact that we are using mat foundation as a base is problematic because in many cases the soil won't allow the mat foundation. That's one issue, and one other issue that's much more costly than common foundations, pipe foundations in some cases. So have you addressed this issue? Because often the top layers of the soil don't allow for foundations, so they are not uniform, so the mat foundation would tilt, for example. So how do you address these issues?
Very good question, thank you. First of all, we didn't claim that we have solved all problems. This is a conventional design on conventional soil, let us say class B of the Eurocode, so this is not applicable, if you like, in soft soil regions. In terms of cost, however, I have to say, because we did that, the cost was a top-up of 8%. With 8%, you solve the problem of quality control, because you don't rely on that. In my opinion, like I said, we haven't solved the problem, but perhaps it is a way to start thinking differently.
Is there any other questions or any comment?
Sure.
Great.
Absolutely. Just to say that we cannot get inspired by solutions that have been used for centuries. The challenge here is how to quantify, to prove experimentally, and then convince an authority to sign off a design. Because by just saying that these ideas have been used in the past doesn't get you very far. But I definitely agree that we're all inspired by solutions all over the world.
Professor Anastasios, thank you very much indeed for your interesting presentation, and once again, this session, I would like to say a couple of things about Ipred. I am proud of Ipred organization. This is not an easy job, and they are doing very good, and I congratulate them. Thanks a lot, and now we have 25 minutes coffee break.
Presentations in the session. Total duration of each presentation is 30 minutes. I would like speakers to respect their times. The first presentation will be performed by Professor Tsunoki from Tokyo University. The title of the presentation is Observations of Japanese Academic Organizations about the February 6, 2023 Kahramanmaraş earthquakes. Yes, please.
Thank you, Chairman, for very kind introduction. Lecturers, distinguished guests, and all of my friends coming from all over the world, and ladies and gentlemen. So today I would like to talk about the earthquake damage investigation conducted with Japanese and Turkish colleagues. Actually, this is quite difficult to use. Go to the next. To the right. To the right. Oh, somebody proud of the USB. Okay. Oh, that's true. I'm sorry, here is Japanese, but it does mean that we, Turkey and Japan, have a long history of friendship. So not only the earthquake engineering field, but also in the several fields. This is one very famous monument in Japan. When the Turkish battleship sank in front of the main island, the Japanese fishermen rescued. So we have not only this earthquake, but also we have the history of collaboration to conduct the investigation. This was the first earthquake for me to join the international investigation, which is a projelerin earthquake. Happened in 1999, very close to Istanbul, and unfortunately the number of casualties was 18,000. Due to the damage, the scale of the damage, Japan decided to dispatch the investigation team. And this figure shows what happened in 1999. Also, the Ban earthquake happened in 2011, and the same year of Tohoku earthquake. Tohoku earthquake happened in March, and in October, unfortunately, the series of great earthquakes occurred, unfortunately, in your country. Then at that time also, Japan decided to dispatch the investigation team. And here, of course, you all may know the location. Not so far from the last earthquake happened in February 6th. You may know Bangkok Road. Then the container houses, of course, there was no place to stay there. So they are very kind to accept us to stay in one of the container houses like this. At that time, the investigation team was just a group of 6, actually 7, but one professor went back one day earlier. Then from Japan, in total, 5 professors joined the investigation team. So that was in 2011, In 2023, this year, unfortunately, the stronger earthquake hit the eastern area of your country. This is the information of the earthquake happened in February 6th. So already there are some speakers introduced the earthquake, so I don't want to take much time on this slide, but two earthquakes happened continuously, almost in the same day. Just the difference is about 13 hours, 9 hours actually, so 9 hours unfortunately. This could happen recently, two strong earthquakes happened in the same day. So they are just examples of the major earthquakes. I'm sorry, it's too small to see, but here, this one is a response acceleration, response velocity spectrum. So you can see solid red line. This red line shows the demand according to the Japanese building code. So from this figure, it's obvious. Even that Japanese building were there, they could be severely damaged. They are calculated by my colleagues in the ERI Earthquake Research Institute of the University of Tokyo. This is one reason why Japan decided to dispatch the investigation team. So, Research Committee on Earthquake Disaster. We have this committee in the AIJ, Architectural Institute of Japan, which is an academic society to deal with building science, not only the building structural engineering, but also environmental engineering, design, planning, everything related to building science. So this committee started to distribute an inquiry to all members right after the earthquake happened on February 6th. Then it's called expanded committee, which means anybody can join the meeting. The expanding committee was conducted on February 13th, about 1 week after the earthquake. Then it was decided to organize a working group to discuss about the investigation team. Then the committee assigned me to be a chairman of the working group. Then during the activities of the working group, the Ministry of Education, actual name is quite long, Ministry of, not Education, Ministry of, I forgot the exact name, but too long, so I'd like to call it the Ministry of Education. So they decided to fund some special budget to deal with the investigation. And also the other academic institutions like Japan, Japan Society for Civil Engineering and the Japan Geotechnical Society, they also came to AIJ to join the investigation team. So we discussed it together. Then we finally decided to go to the affected site from March 28th to the April 4th. Then we contacted with Professor Alpelviti of ITU to organize the investigation team. Then he recommended us to be based in Gaziantep. Then leader from Turkish side was Professor Alpelviti of ITU. Then from Japan, 27 researchers joined the investigation team. This was actually the biggest investigation team in our history of AIJ. Then according to the number of Japan side, the Turkish side kindly organized quite large investigation team with 22 researchers. Because of such a big team, we can investigate not only usually we just investigate the damage of reinforced concrete structure and the masonry structure. But this time, we have a lot of researchers, so that's why we decided to investigate not only the reinforced concrete structure, but also steel, wall type structure, hospital, base isolated building, geotechnical damages, and so on. This is a member list from Japan side. It's a big table. So I'm the leader of the investigation team, and 26 more researchers came from several universities and private companies, and some were coming from the confirmation bodies, which gives the approval to the project of building, planning and development project. So this is a list from of the Turkish side. The leader was Professor Ilki. Then there's so many researchers, some of them are right here, joined our investigation. So target area, already you saw this similar pictures during the presentation by the previous speakers. The distance between from Antakya to the northern end was Malatya. The distance is about 350 kilometers. It's quite long. But unfortunately, if we go this place or this place or this place, always you can see the quite severely damaged buildings, unfortunately. The first earthquake happened here, and the second one happened here. The firstly, one group investigated the situation of strong motion observation stations, and also they conducted the building by building investigation to see what is the damage condition. Then if the condition agree with the measured acceleration or not. So you may know the AFAT opened the several strong motion data, but several days after the earthquake, they once closed the homepage to scrutinize the data. Then finally they decided to withdraw some data. I would like to show you some examples. Then this one is recorded acceleration at this station. Then we calculated the the seismic intensity according to the Japanese standard, then which that was 6 plus. It's almost highest. The highest seismic intensity is 7. So it's quite strong shaking. Then actually the PGAs in each direction are shown here. It's huge. Then this one is calculated demand curve. According to this figure, for sure, even Japanese building can suffer severe damage, unfortunately. Then they conducted a one-by-one investigation according to the European scale, 98. Then which can classify the damage level from 0 to 6, as far as I remember. Then the collapse ratio is the number of the building classified from 3 to 5 to the number of investigated buildings. For this station, 28 buildings were investigated. Then amazingly, 54% was the collapse ratio. It's a huge number. So for sure, shaking itself was too strong. Unfortunately, today, because of the time limitation, I cannot show you the whole results. So I'd like to move on to the other group. The other group is the technical damage investigation group. Then, sorry, some are in Japanese, but this one is Iskender. Already the previous speaker introduced this portion. In front of the sea, then they told me this is not artificial land, but somehow gradually it became a land. That area used to be under the sea. So that means the water level is quite high and soil condition is not steep. Then, as a result, we observed a lot of the uneven sinking of the building and also a liquefaction. And also, you may know that unfortunately, after the earthquake, heavy rain hit this area and the flood happened. And also, this kind of a landslide happened. Then I read a report which said about 3,600 landslides were observed due to this earthquake. Then Gyeolbasi is the name of the city. In front of Gyeolbasi Lake here. So that means, that sounds like the soil condition is not so steep. Then actually the water level is about 1.5 to 2 meters below the ground surface. Then unfortunately, most of all buildings don't have the pile foundation. They told me that they excavate the ground to see the water level. Then they put a foundation there, the direct foundation. See? Then what happened? Of course, the liquefaction occurred. Then the building sunk unevenly. Then here is the street. Then you can see that most of all buildings are inclined a lot. Then this figure already introduced by the colleague, the previous speaker. And this building actually the sunken and also the story failure occurred in the ground story, unfortunately. This one is also different street of the same city. You can see many buildings inclined a lot. This one, the story failure also happened. Okay, let's move on to the reinforced concrete buildings. Fortunately, this was terrible. I'm a reinforced concrete guy. My research field is reinforced concrete structure. Then when I was a PhD student, the Kobe earthquake happened. I was dispatched as the youngest investigator to the affected area. Since then, I was dispatched to the earthquake affected area not only in Japan but also all over the world, like Chile, Peru, and many other countries. But always I thought, the damage was catastrophic, devastating. But if we say what earthquake was severest in terms of shaking, I always answered Kobe earthquake. During the Kobe earthquake, so many buildings collapsed due to just strong shaking. But this earthquake, I think, worse than Kobe earthquake. If we look at the buildings in the city, you see actually this is the situation. Not only this city, but also if you go some different cities, still you can find out that almost the same situation. Many buildings collapsed. And you see the pancake collapse happened. Probably this kind of building could be the old building, then the big column strong beam mechanism. Then unfortunately the pancake crash happened. But even the buildings designed according to the current building code, they have the very proper weak beam, strong column mechanism. But the shaking was too strong, then some buildings overturned, unfortunately. The shear failure, brittle failure didn't occur, but still, due to the strong shaking, they overturned. One reason could be the too much reinforcement, especially at the bottom of the column. You may know that the column dimension in Turkey is somehow very unique. Very thin, looks like wall column. but the earthquake load is very high. So as a result, we need to put a lot of reinforcement. Then usually at the bottom of the structure, we have the joint of the reinforcement. Then the amount of the reinforcement becomes double. Then you see this one, there is no space between the lever. The concrete cannot be cast properly. Then there is no bonding action between the concrete and the steel. This could be one reason why the structure turned over from the bottom of the structure. Actually, this building was designed according to the current building code. Then this one also quite similar, the overturned. See? But this one and this one and this one, they are a pancake crash. So probably designed according to the previous building code. So one example, this photo shows the apartment complex in Iskender. Consists of 7 quite similar buildings. They were designed according to the current building code and quite new apartment buildings. Then here you can see the direction of severe damage. See? Then Then some of the damage show the foot fractures. Then the joist slab was applied. Joist slab is the slab which was presented by the previous speaker. There is no beam. Just looks like flat slab. But actually the flat beam is arranged. Then in between the flat beams there is no concrete slab. And you see this is the bottom of the column of this apartment buildings. And again a lot of levers arranged, then the spacing between bars is not adequate. And of course some fracture happened, and also in some beam column joint, the lever is going outside of the hoop. So that means the main bar was arranged outside of the core concrete. Here you can see the 15-story reinforced concrete building. That was severely damaged during the first earthquake. Of course, I was not there during the first earthquake. So the people living here told me that during the first earthquake, after the first earthquake, the buildings were still standing. But during the second earthquake, unfortunately, they turned over. Actually, not this building. Here, there are 2 buildings around here. Then they overturned from the bottom of the concrete of the building. Oops. Then this is the situation. A lot of the bars you can see, and I need to accelerate my presentation because 20 minutes already passed. Then also some researchers conducted the research on the business continuity, like factories. Factories, even if the factories are okay, but the inside we have a lot of equipment. If they cannot be used anymore, that means that they need to shut down the factories. So we investigate. And also the base isolated hospital also already introduced this hospital worked better. We also conducted a damage investigation of masonry buildings. The Gaziantep is one of the very important and historical cities in Turkey. There are many historical national heritage masonry buildings. They are very old, but some historical buildings survived without any damage, but some collapsed. We have also new masonry buildings there. Then some again severely damaged. What's the difference? The old structure was okay, but the new masonry structure collapsed. that's quite an important point. So we decided to dispatch another investigation team to investigate the reason why. Detailed investigation, we selected 25 buildings to conduct a detailed investigation, which means we measure the size of the columns and beams one by one. We measure the span length, we measure the concrete strength, we try to get some sample of steel bars, then conduct the damage classification, or let's say rapid inspection, according to the Japanese standard and Turkish standard, to compare the result. We are still working on this. Then so far, the 10 buildings were classified as severely damaged. Then one was okay, no damage, 4 slightly damaged. Sometimes, if we go to the affected area, we wanted to investigate only the damaged buildings. But that's not a good idea. We should investigate not the damaged buildings as well, to find out the reason why the building was damaged and why some buildings are not. So in that sense, we selected not only severely damaged building, but also moderate, minor, and slightly damaged buildings. We are still working on this. Then right now, my colleagues are in Gaziantep working to measure the size and to conduct a microthermal measurement, because they are going to develop the numerical model to conduct the simulation. Then just show you one example. Here is one apartment complex consists of 4 buildings. The dimensions, planning are almost the same. Only the difference is the number of stories. Under construction, nobody was living there, fortunately. Then one building totally collapsed here. Then another building, first story was gone. It looks like okay, but for sure, first story was gone. Then C, inclined a lot. Then D, standing. This one is building A, totally collapsed. Then again, there are a lot of barrels at the bottom of the building. B, it looks okay, but if you get closer, you can find out, oh, first story was gone, unfortunately. But this one was designed according to the current building code. Then C, you may recognize it inclined a lot towards the left side. We can see a lot of the very ideal failure mode of the beams. Right? For sure, the yielding hinges occurred, but unfortunately the deformation was too large. Then eventually the shear failure occurred at the both ends of the beams. We conducted the damage classification or rapid inspection, and also we measured the inclination angle. 6%, it's a huge number. The building D looks okay, but of course the least damage, but the moderate damage. Like this. Yeah, moderate damage. Then also some researchers conducted the research investigation on the code system and recovery. They visited the city halls to ask how they confirm the calculation and the project, how they give the permission, and so on, and also how to recover the affected area. So concluding remarks, yeah, it's almost the time. International joint investigation worked very well due to the Turkish researchers' elaboration and very kind support. Then also we also conducted, we are conducting detailed studies together right now, as I told you. Then damage classification method of the Turkey and Japan will be compared soon. We are also planning to publish the joint reconnaissance report in the end of this year. Then after this slide, there are a lot of the lessons and problems remaining. but tentative. They are still on the table of discussion between Japan and Turkish researchers. There's no time to read one by one, so I just quickly skip. You can just see so many lessons we obtained from the first day. For sure, this slide will be open on the web page, so you may have the chance to look at the slides in detail. So for each investigation topics, we listed up the lessons and problems we observed. And acknowledgement, Japan Embassy in Turkey and JICA, and AFAD also, and so many universities and researchers in Turkey. We couldn't conduct the research without their strong support. I would like to thank all of them again. Thank you very much for your kindness.
Thank you, Professor Sumoki. Any question or comment?
Professor, microphone is coming.
Thank you very much for your detailed explanations. I would like to know, where was the location of the beams with two plastified zones at the ends? Were they located between two shear walls or where? Do you remember that?
You mean these kind of damages?
Yeah, that's right. Are they located in between two shear walls or not?
Oh, actually, this is the plan. Then this building is almost open frame structure. Then this building didn't have a lot of shear walls. So these kind of damages occurred just both ends of the beam, no matter if they are connected to the wall or not. But if we compare with the Japanese building, these currents are very similar to the wall, because the length of the current is quite long, then the stiffness of this current is very high. So that's why somehow this kind of damage could occur easily compared to the conventional, the open frame structure in the world. Please. Oh, the microphone.
You show the plan view of ABCD blocks. Can you show that map? And there is an arrow showing the direction.
Yes.
Not this one, the sketch of the ABCD videos. Like a map.
This one?
Not the drawings one, maybe. Yeah, maybe. Well, they're just showing the six of them.
The different apartment complex, right?
Yeah.
I see.
Yeah, that's right. Yeah.
This one.
Right. And then there's another block, you're showing the direction, this is the direction of motion of the earthquake, or what?
This one is the severely damaged direction.
Okay, the another map you show a marked specific direction. This is the direction of motion of the rupture from, and if that's so, we have ABCDs, severely damaged, but he's standing up. So what's the reason that's not damaged much, or standing almost structured with respect to other ones? Orientation matters as far as the design purposes on the ground, as well as all traces and so on, you name it.
I see. Thank you very much for your question. Actually, we are not thinking that these directions are coming from the earthquake itself, but the planning of the building. Then looks like square, but the plan, the arrangement of the shear wall is different in each direction. Then this wall always suffers the severe damage. that wall is in this direction for this building. Then the plan of the building rotated 90 degrees for this building. That's why the damage concentrated in this way. So in other words, only this wall suffered severe damage. So these arrows are showing the direction of that wall, not because of the earthquake or shaking. Yeah. That's what we are thinking. Yeah.
Okay, we have 10 minutes delay. Thank you once more.
Later.
Professor Kusunoki.
Small question. Okay. If the chairman allows.
I appreciate for your nice presentation. My name is Mücahit. I'm from Medya University. I just want to ask, according to your observations, did you see any totally collapsed building that has a basement with shear walls?
Basement with shear wall.
Is any building that collapsed which have a basement with shear walls? For example, REs have any basement with shear walls or not?
I see. Unfortunately, we didn't try to get into the basement of the collapsed building. So, unfortunately, my answer is I couldn't conduct this investigation on that aspect. But probably Professor Raul will talk during the Chilean earthquake. It happened. Raul-san, okay.
Okay. Thank you, Professor Sumoki.
Next presentation will be conducted by Dr. Patrick Christoph Mayer from University. The title of his presentation is The Hidden Reason Behind the Massive Destruction Caused by the February 6, 2023 earthquakes.
Hello, everybody. Thank you for having me. Yes, I usually walk around a lot, so as you can see. I have a strong background in engineering, but today I will talk about what I consider a serious and dangerous blind spot in the engineering community and in the society in general. So while we've been talking about a lot of technical issues, I think that the real reason why the damage was so large, both human and material, was not an engineering issue, but a social issue. So I will start the presentation talking about what happened, not in general, but with the dominant failure mechanisms. And I will show that those failure mechanisms were known and the solutions were known. And despite of that, they happened. So the question that you start asking is, why did they happen anyway? So I will try to answer that question. Besides my engineering background, I have a strong background in neuroscience and try to understand why people make decisions in one way or the other. So I try to explain that without going into neuroscience too much. And then I will end trying to propose a way to start modifying the situation that I think dominates a lot of the events in earthquake areas. So what happened? So most of us, I think, are very familiar with what happened, so I will cut it short a bit. But I will go into 5 or 6 failure mechanisms that dominated most of the failures. And most of us will recognize them very easily, and we will have a list of solutions to this problem. And even the building code, the Turkish building code, addresses them. So we have to start asking why they happen despite being very familiar to us. So soft story, it's a very common story. happens over and over and over and over in every earthquake, and it was maybe the dominant one in this earthquake. By the way, I went to the earthquake region 1 week after the earthquakes, then almost 10 days, and then I went back a month later to spend 2 weeks by the invitation of some government, the local government. So the soft story problem is well known, well documented, and we have plenty of solutions to prevent that still happening. We have been talking about liquefaction, very well known, very well documented, still happening again. Low sheet capacity, and we are talking about new buildings, also very well documented. The Turkish building code addresses this issue very effectively, so it should not happen, but still happen extensively. And this, in some regions in Kahramanmaraş, we have entire new buildings all damaged. Some collapsed, some didn't, but this type of damage should not happen. We know it happens, why it happens, and we know how to fix it. Why didn't we fix it? Why didn't we build it the right way? Short column problem, mostly latest building code in Turkey, but many buildings had this problem, that the short columns had in fact too much shear force. And again, it's a well-known problem, and it should be retrofitted, because I guess in new buildings they don't make this mistake, I hope. It's too obvious. But it was not addressed. And we're talking about a region that is not a poor region, right? In many cases. Lack of ductility in general, either because of excess of reinforcement at certain points, or because it was poorly designed or poorly implemented. Extremely common, extremely common. Obviously, the contractors, the workers, I think the engineers understand this well, but in the implementation phase, this might vanish and ductility will be lost. So we have to see massive girders connected to slender columns, things like that we should never do. But it happens on a very regular basis by the thousands of buildings that were affected by this issue. So it's a known problem with very clear and known solutions to this problem. Why did it happen so extensively? Poor design and materials. Again, we know about symmetry, about having the center of mass with the center of stiffness, and all these issues were completely ignored in many cases. And it was very disturbing to walk along the avenue and see pancake after pancake after pancake after pancake. And knowing that it should not have happened. We know how to do it, so it wouldn't happen. So the problem is known, the solutions are known, and happening again. So it's not a technical problem, because we know the solutions, and the solutions are feasible, for Turkey at least. Malpractices, all the time, everywhere. These are things that are not acceptable. Excess of rebars might be an issue that could be forgiven in some ways, but the lack of rebars is not forgivable, and if it's consistent across many of the failures, we should question ourselves, who is building this thing? Who is supervising this construction? So there were many situations that anyone with a little knowledge about structures, any worker, mason, would understand this is wrong. This is simply wrong. But it was done systematically. Then we have the lamination issue. This gets a bit more tricky, but Turkey has a lot of experience with historical buildings. They have retrofitted numerous tricky structures effectively and successfully. And in this case, maybe they were ignored or hoping that it wouldn't happen here. But obviously we knew it would happen because Hatay and all this region is very seismically active historically, so we should have acted preemptively, not waiting for the earthquake to wake us up and say, let's do something about these structures. Another group of structures that was severely damaged were the industrial structures. These are trickier because each of them might be different. There's no standards that we can say how to do it or not how to do it. But given that Turkey has some of the top engineers in the world, and some of these structures are extremely expensive and valuable to Turkey, maybe a better job should have been done. What was not acceptable for Turkey, having such a long history with historical buildings properly built and resistant to earthquakes, that we had so many stone masonry buildings in expensive areas. This is not rural areas, these are expensive areas that were built with like rounded stones and things like that, with no proper reinforcement. And I say expensive areas, very expensive areas in many cases, and these buildings were not preemptively retrofitted in some way or the other. And finally, the rural areas, there I cannot be so harsh because people have many problems in rural areas, but the construction practices in rural areas were very poor. Obviously the lamination again, using very small stones, but we know perfectly how to build proper stone houses that at least will not collapse in most cases. And the villagers were not informed properly, and there's a large building stock in Turkey that is affected by this. You have historical buildings in the villages and so on that were built properly, so we know, you know how to build it properly. But in new houses like 20-year-old, 30-year-old houses like these ones, these practices that were traditional for Turkey have disappeared. So let's go back and recover them. So basically what happened that known problems were the main structural weaknesses, were the main source of collapse of the buildings, and these problems had known solutions, and that these solutions were accessible to Turkish engineers, but they were not implemented. So why were they implemented? Why these problems that are so well known and have so clear solutions were built poorly? So some people would say lack of materials or economic resources. It's not right. Turkey is not a poor country, and the region affected in many cases were not poor regions. Lack of previous experiences, no. We know all the presenters talk about it. It's a very active region, seismically active region. Lack of engineering skills, no. ITU is one of the top universities in the world in this sense, and there's many Turkish engineers that fully understand what's going on. Lack of building code, no. The recent 2007, and I think this is even a newer one, fully addressed most of these issues. It's true that the intensity was very high and some damage was to be expected, but not at this grade. Governmental supervision, theoretically there is a supervision of the construction process, but it seems that it has been bypassed in many ways in different manners, with amnesties and all kinds of things that should not happen. And I will go a little more into this. So there's no real excuse, either material or knowledge or experience, and so there's no reason for having these type of buildings stock present on Turkish lands. Just to give you an example, next to this building there's a Toki building, a new building. There's hundreds of thousands of housing units in the region that was affected by, or 133,000 housing units. None of them collapsed. None of them collapsed. Most of you know Toki is low cost, subsidized housing from the government. So Turkey knows perfectly how to build seismically resistant buildings, housing. Toki did it. None collapsed. Usually Turkey is the exception, not the rule. So Turkey has all what it takes to build proper housing, proper structures. The problem was that maybe the individuals try to cut corners, not just to make money. It's just the bad habits, maybe, sometimes to make money too, but usually the construction is not cheaper when you do it wrong than right. Sometimes it's to fatten profits, sometimes it's just carelessness. Then we have these inspection firms that are not inspection firms anymore because they also bypass the law and they get paid. Even the same construction companies, they set up their own inspection firms to be inspected by themselves. Government grants amnesties on regular basis by the hundreds of thousands of buildings. So you turn a building that is not safe into and it's rightly so, not safe. So it should not be sold. But now just by paying a fine, suddenly this building can be sold and is legal. So you are not selling apartments, you're selling tombs, basically. You know that in the next earthquake, this building will collapse. You know it. The government knows it, the engineers know it. So you're selling houses that are not houses, are tombs. So, in the end, the whole community, from the top government to the lowest worker on the construction site, are aware that things are being done wrong, but no one is stopping it somehow. Why is that? So, why deliberately we are doing things wrong? So, I would call it the elephant in the room. So, I don't want to insult anyone. The Turkish society, culture is extremely interesting and beautiful and has many good positive things. But like any healthy body can have some kind of sickness, illness. Turkey has a serious problem with ethics or lack of ethics. Ethics not only corruption in the sense of money, but in the sense of being careless, in the sense of lack of respect. Because if you know that your work could cause the death of a family, you would be a bit more careful than what's being seen as something, a common practice. So, the fact is that in the whole construction structure, there's a deliberate common ignoring what's being done that is wrong. So we know it's wrong. We know. There's no one in Turkey that doesn't know that it's not wrong, but it's still happening regularly. So how do you fix an ethics problem in society? I'm also a professor at the university. I know students, a lot of students here and in other countries, and I also see this lack of ethics in daily basis, in their homeworks, in their, and this has to be addressed from the very beginning, from the universities. So education, the problem is education is led by professors, and professors were trained by the system. But obviously, we give a lot of emphasis on transferring skills to students, and we forget about ethics and discipline and critical thinking, because we focus on nice, fancy software that gives us colorful solutions to things that we don't understand. So I think education should refocus on ethics, number one. A person without ethics is a danger to society. So make sure that your students in the future have strong ethical values and strong discipline and strong critical thinking. Then it can be anything they want. But if they miss these three, these people are either useless or dangerous to society. So please, those who teach, look into that. Public and engineers, they are also responsible. The public in Istanbul, they know, they just mentioned 70% of the buildings in Istanbul are not safe. We know that. 99, we had a warning. What has been done in Istanbul? Nothing. Nothing.
I know the solution is complicated, but you need to start solving the problem. People should go out in the streets and ask for a plan to solve this problem. They are living in houses that could collapse anytime in an earthquake. So public should take more action and be more responsible for their own decisions. And government, I think government is the only realistic short-term improvement that can be introduced in this system, is to really very strictly enforce the current building code, or maybe improve it a bit, but it's the enforcement that is missing. You have all the tools. So please, government officials, make sure that you have a system in place that will make that the design is what is being built in the field. You have all the tools you need. You have the technical skills, you have the money, you have the experience, you have the engineers. So make it happen, and you need to punish, because society, you cannot change it in one generation. It takes generations. So, but the government can interfere very drastically, very high punishments to dissuade these malpractices. So, what happened is that the dominant failure mechanisms that we have seen in this earthquake were known, and the solutions were known and feasible. Everything was available to build properly. I think that the reason why it was not done properly is from the bottom to the top, and from the top to the bottom there's an issue in the society that allows for malpractices and corruption in some cases to modify the design and the implementation of projects. So I think that many of the deaths that happened were not accidents but are homicide, because they were done on purpose, knowingly. And a lot of the loss was not an accident, but it was theft. And I'm sorry to use these words, but I cannot find better words. So how to deal with this? Education is a more long-term solution, and I really think that hopefully Erdogan's government will become even tougher on the construction community and enforce already a very good building code that they have in place, and the supervision system with these companies that are supposed to supervise the construction, and make it a reality that the future Turkish building stock will be safe for everybody. Thank you very much. And any questions? Sure. Please.
and came together and decided we have to stuff. one simple parameter, and that was limited the drift ratio to 0.2%. 0.2%. In their report today, I hope that's taken to say I'm wrong, but you have asked all. In their report, you speak about shareholders, but implement the 0.2% ratio criteria, you cannot do anything as part of the shareholders. And this has been going on for decades and decades, and even in the last decade, the same 0.2% exists. I presented this kind of suggestion or talk, let's say, showing an example at 1 year after the 100K, and also in March in London, several times. Examples to experience how they succeed, and I think Turkey can. If the data from is here, maybe you would like to add.
Thank you for the comment, very interesting.
Okay, thank you.
Third presentation will be performed by Professor Gürkan Özden from 9.Eylül University. The title is Geotechnical and Foundation Engineering Issues in the February 6, 2023 Kahramanmaraş earthquake based on field surveys.
I would like to thank the organizing committee for the kind invitation to this symposium. I'm going to talk about our observations, and based on these, I'm going to apply some geotechnical and I'm going to underline some geotechnical and foundation engineering issues in Kahramanmaraş earthquakes. This one. Scope of the presentation. Shortly, inadequate foundation response mechanisms during earthquakes. Response of shallow foundations of fatal buildings on firm soils. I prefer to call such buildings as fatal buildings. Those examples will be from Diyarbakır. Geotechnical problems originating from alluvial soil behavior in Hatay, and then comes problems, and my presentation will conclude with conclusions. Well, talking about foundations, we have two types: shallow foundations and deep foundations, and their response is affected by either poor ground response or structural damage to the foundation. can see here, these examples are from Gölbaşı. This famous one on the left-hand side, everybody thinks that it is because of the liquefaction. I think I am not sure about it. Probably in a very low factor of safety against overturning was the cause for this building. And here on the right hand side, however, we see really liquefaction related damages to buildings. So in order to analyze, in order to determine these problems in advance prior to the earthquake, our job is simple. Just conduct liquefaction analysis, bearing capacity analysis, select a type of shallow foundation, make sure that the connection beams, if you use C3 foundations or footings, connection beams are rigid enough, and construct your building. If you need, you may apply soil improvement. High foundations are little more complex, or more complex, I should say, because the piles may be loaded by the soil, either during the earthquake or after the earthquake, when the liquefied soil laterally spreads. This famous example is from Niigata. The laterally spreading liquefied soils just apply drag force and normal force on the piles, and the shorter pile completely embedded in the liquefied soil face damage at its head, and the longer one, however, it is suckered into the non-liquefied soil, and it faces both at the interface, around the interface zone and its head. Also, inertial laws are another factor for the piles. They did, the Japanese engineers, researchers pulled out the piles from the ground and investigated the cracks, and this one is these damage photographs are from Kobe earthquake, and these failures are due to inertial loss. The ground did not liquefy. However, we can see that, I guess I wasn't there, of course, but my sense is that the trailing piles experience damage over there. So inertial loss and kinematic loss and lateral spreading are causes for pile foundations. Although they can face damage, piles usually save the building during the earthquake. On firm soils, response of shallow foundations on better buildings on firm soils. So I will not read out the entire text over here, but we, as a team from 12.ULUSLARARASI University, we had a chance to work on 6 totally collapsed buildings in the Diyarbakır.
and there were claims. The contractors, this is usual, contractors, and sometimes the residents of the buildings blame each other about column cuts. So we went there and using excavation machines, we just got rid of the dirt, and this was, I will not give the names, even on the news during the summer. And you can see that this is grid foundation, and it behaved very well. Why? Because the building was so weak that it collapsed in the early stages of the earthquake, and did not have chance to transfer inertial loads, and the foundation stayed intact. This is another building. We were able to find out the basement column layout of the building, and you can see that the collapse moment of the structure during the earthquake. This is the Diyarbakır Bağlar 2101 station, northern component. The peak ground acceleration is so low, 0.08 g. It's so low. And on the very right-hand side, we see the old picture of the building. I should mention that this building had its legitimate construction purpose, but just for 6 stories. And somehow, some way, they built 11-story high, and it collapsed. And the foundations of this building was footing type, and it is all in place. It was all in place. Nothing happened to the foundation. For the alluvial soil behavior, on the other hand, to my knowledge, there are just 2 examples. The Hatay and Adıyaman provinces. This picture is shot, it was shot in İskenderun. There is a recreational pier at the city center, and the ground subsided after the earthquake, which is post-earthquake, post-liquefaction settlement, undergrowth 100 to 150 centimeters, and we are lucky to have a earthquake strong motion recorder in İskenderun, and the peak ground acceleration was not that high. On the other side of the Amanos mountains, we see a huge peak ground accelerations, really huge ones. But this much acceleration was enough to trigger some liquefaction, but not too high to topple down buildings and other things. I didn't see along the coastline as far as I was wandering around the city center. Just limited settlement occurred. On the other side of the Amanos mountains. We see several liquefaction traces, fine sand, clean fine sand, and the peak ground acceleration exceeded 0.6 G at most stations. And it happens that, I guess, the unluckily, this one, the airport within the red circle might have affected by the liquefaction as well, I should say that. The Adıyaman, I spent quite some time in Adıyaman, and this is the full official structural damage distribution in Adıyaman city center. Almost all of the structures were either moderately damaged, were tagged as either moderately damaged or heavily damaged. And Adıyaman, strange enough to me, did not take attention of the researchers so far. My feeling is really severe soil amplification took place over there. We need to consider in this way Adıyaman. And there were almost no buildings left to stay in the Adıyaman city center. And Gölbaşı, famous Gölbaşı, it is liquefaction stories, and this is the official damage distribution of the structures. Just a small number of buildings completely collapsed, and the rest either tilted at varying degrees or settled down. Had there been no liquefaction over there, probably we might have seen higher life loss in Gölbaşı. The liquefied soil worked some sort of natural isolator here and protected the buildings from total collapse. This is the active fault map from earthquake research of AFAD. In Adıyaman, parsec border coordinates were shifted by 1 to 2 meters towards west in Adıyaman. Why? Because Adıyaman stays on the Arabian plate, and the other side of the Gölbaşı Lake is on the Anatolian plate. And I'm not a tectonic guy, but I was paying a closer view to the active faults. The East Anatolian fault has some shift over there. Maybe the Gölbaşı was, in this sense, at a bad place. And this picture was taken from Balkan. We see 3-meter fault structure over there. The strong motion recorder in Gölbaşı stopped recording during the earthquake, unfortunately. We lost all the data over there. And the closest station is in Pazarcık, and the peak ground acceleration were on the order of 0.6 maybe. What is soil conditions? We set a micro tremor campaign over there. A total of 32 readouts were made in Gölbaşı. We had a chance to reach quite comprehensive report by İller Bankası, İlban right now its name is, and in addition to that, we conducted 5 additional boreholes and we did some laboratory index tests. Strange enough, the soil is mostly consisting of clay soils. These soils were not expected to liquefy according to current liquefaction analysis methods. And we can see that all the clay exists there, the SPT flow counts are low. We cannot retract them clearly, but it varies between 2 to 6 down to 8 meter depth, and then gradually increases. However, the clays were either identified as low plastic clay or high plastic clay. And the clay content of sands was large enough, like more than 30%, which is another interesting case in this sense. We managed to set natural period distribution of Gölbaşı based on our micro-tremor readouts, and the reds on the corners and edges are erroneous. We need further measurements over there. So 5 seconds may not be correct according to me. But we see that there are 3 rivers carrying sediments into the lake, starting from old times, and we expect the base, the engineering bedrock at about 80 meter depth, and the base rock may be encountered 300 meters below the ground surface. We need to work out. These are the liquefaction pictures we see. The majority of the structures punch down into the soil, but they did not collapse. Most of them did not collapse. So saving lives of the people. The school buildings behaved well. All of them has, each one of them has at least 1-story basement. Okay, they did exhibit post-liquefaction settlement at varying degrees, but even we don't see major tilting on these school buildings. Lifelines were damaged. My colleague will make, I guess, much extensive presentation about lifelines in the earthquake, lifeline damages in the earthquake. And lateral spreading took place, a recreational facility, official government-owned recreational facility, just slid down into the lake, and we had a borehole over there, a new one we conducted, and I numbered it as DSK2, and we can see that it is clay, low plastic clay with some sand content, and sand content this time it is also considerable, 20%, 30%. So we need to study the transition from sand-like behavior, clay-like behavior, or clay-like behavior to sand-like behavior. This is an interesting topic, and it is not only related with the consistency of the clay or density of the seeds, it is also related with the earthquake intensity, I guess, earthquake energy. We conducted unmanned air vehicle survey at the federally facility inside, only above the federally security facility, and over there I got four section cuts. We can see that the scale is kind of fuzzy, but we see that the ground subsided, spread it towards the lake by 2.2 meters, 2.5 meters. And these are the pictures from the secret zone. And we used UAV over here just because it is not possible to take dependable elevation measurements using conventional methods. So the UAV helped us a lot in this sense. There are some other things that could be shown or talked about. I cut them. The most important thing in terms of researchers is the passage to sand-like behavior to clay-like behavior. The Gölbaşı suffered life and great economic loss due to extensive liquefaction and softening of alluvial soils. Residential and school buildings behaved quite well, according to me. They showed less settlement and tilting compared to residential buildings. Iskenderun experienced lower accelerations, and the underlying soils did not, according to me, completely lost their shear strength, because we even observed post-liquefaction settlement in 2020 Samos earthquake also. It happens, even at small acceleration levels. The jet grouting applications and pilot foundations played a positive role during the earthquake in Iskenderun. Liquefied soil sites of Antakya, which are on the other side of the Amanos mountains. Luckily, they were not that much heavily populated. The airport runways seem to get some damage due to the putrefaction. And for the other examples, if the superstructure is weak, it cannot transfer inertial loss to the foundation as it collapses at early stages of the earthquake, which is very expected things. And I would like to show some things. We took this picture in Gölbaşı. It is said, bu evi yıkarken nazik davranan, mazilere sığmayan anlar. It is an unforgettable memory for us. These are the names: MK, MZ, AZ, and MK, MZ, AZ, kendilerini de burada anmış olalım. Teşekkür ederim. Buyurun.
Thank you. I read a report that recommended a mat foundation, but the geologists made this recommendation. I believe that if the proper geotechnical investigation is made and they recommended at least the basement for this in this sort of condition, I believe that this sort of damage wouldn't go there. So the geotechnical informations for the houses, if the foundation system was a little bit deeper with a basement, I believe that this kind of result wouldn't be happen. What do you think?
Yeah, right. We observe similar positive response for such structures also. That's correct. However, the government decided to shut down maybe they are right, because it is right now, it is very easy to improve the soil over there. Is that during the dynamic compaction machine, replace the poison soils with large chunks and but mainly addressed by us will have on this method. They are, to my knowledge, they are having a hard time to find out the outline inside this which is also known as the set and development.
Thank you once more, Professor Özlem.
The last presentation conducted by Sezer Öztürk, the Professor and Professor from Istanbul Teknik Üniversitesi. The title of the presentation is Performance of Industrial Buildings in February 6, 2023, Kahramanmaraş Depremleri.
Dear professors, dear guests, hello and welcome. I would like to thank those who contributed to this valuable conference. My name is Sezer Öztürk. I'm a PhD student at Istanbul Teknik Üniversitesi, Structural Engineering, and I am in my thesis last stage. My supervisor, Professor Dr. Ali Sarı, could not attend today the conference because he is abroad. So I will try to present this study. Our topic is performance of the industrial buildings in February 6, 2023 Kahramanmaraş earthquakes. We also conducted a field survey in February. Our research team is also big in background. Our presentation content includes these hearings. I will make an introduction and provide details for the industrial structures we examined in the field. I hope to complete the presentation on oil storage tanks, maize silos, prefabricated structures, also low-rise steel structures and results. As we all know, major destructive earthquakes have occurred. Thousands of people lost their lives, unfortunately. Numerous aftershocks occurred. The destruction was huge in many cities. Hatay, Gaziantep were some of them. It is thought that near-fault effects and soft soil effects are also effective here. In this presentation, I will try to explain industrial building performances. I will try to present the structural behaviors we see in Gaziantep and Hatay provinces. First is the oil storage facility in Gaziantep, Nurdağ. There were many cylindrical steel storage tanks here. We also saw different types of damage. Damage such as wall buckling, damage due to sloshing, liquid sloshing, overturning due to insufficient anchorage, shifting and bending of base plates were encountered in the field. This region was close to the 2712 accelerometer station. We also examined this data here. Of the tanks marked right picture, the left one suffered sloshing damage. Tank in the middle collapsed due to insufficient anchorage. In the tank on the right, a buckling occurred in the lower layer of its wall. Now we will see in detail these tanks. Here in the figure there is a tank with damage due to lower layer of its wall. A buckling damage has occurred. The height of this tank is 8 meters and its diameter is 5 meters. We obtained information in the field that the filling ratio was around 90%. Accordingly, the impulsive and convective periods of the liquid in the tank were calculated according to different seismic codes, and these values were obtained as 0.19 seconds and 2.34 seconds respectively. These values are available in the table, API, Eurocode, Turkish Tank Code, Architectural Institute of Japan, these seismic codes. In addition, a three-dimensional time history analysis was performed with the same geometric and material properties, and 27 were acceleration record values. The real situation was modeled exactly, and damage was obtained in a way similar to the real situation as shown in the figure. The coupled Euler Lagrangian method was used to model and liquid structure interaction, and general content was defined in finite element analysis. Verifying the damage caused by the earthquake through numerical study is considered to be an important output. The acceleration record is as shown in the figure, left figure. PGA value is 0.6 G. For this tank, since there was damage to the lower wall layer, impulsive motion of the liquid acting with the tank dominated, and its period was 0.19 seconds. Acceleration spectrum values are presented in the graph on the right. Spectral acceleration values of the earthquake around 0.19 seconds exceed the spectrum values provided by the seismic code in the region. This can be an idea the cause of the damage. In addition, this damage could be predicted with high approximation with the fragility curves we derived for cylindrical storage tanks from our previous numerical and observational studies. Damage state 2 for 0.6 G acceleration could be predicted with 85% probability via fragility curves. Here left graphs have only observational data, right graphs have both observational and numerical data. And another damaged tank is shown in the figure. Here the upper layer and roof of the tank were damaged due to the sloshing motion of the oil, vegetable oil. Its diameter is 6 meters and its height is 7.5 meters. Similar calculations were conducted here, and the convective motion of the liquid dominated for this tank. Its period is around 2.5 seconds because at the upper levels of the tank the liquid moves freely and sloshing motion prevails. The period of this motion is also expressed as the convective period. Similarly, when we look at the spectrum graphs, we see that the spectral acceleration values provided by the seismic code for the 2.5 second period are exceeded. Here too, the cause of sloshing damage can be understood. Likewise, this damage could be predicted with high probability in the fragility curves. In addition, in literature, in many studies, high values of acceleration in the spectrum graph for periods longer than 0.5, 0.6 seconds indicate that reactivity effects here are present also. It is also seen here. This is also one of the effects of the earthquake on the structures. maybe in here spectrum graphs, we can see amplified values after the 0.5, 0.6 seconds values. Also, different tank damages in the oil storage facility can be seen here, such as a tank that topples over due to lack of anchorage, a tank with diamond shape buckling on its wall, or a tank with a slipping and bending base plate due to severe shaking. These examples can be increased for this facility. Conclusion for the oil storage plant facility. In the vegetable oil storage plant, it was observed that one of the tanks was buckled in the lower part of the wall, the upper part was damaged by the sloshing effect in one tank, and one tank was overturned due to insufficient anchorage strength. Impulsive period for the tank with buckling in the lower wall layer, 0.19 seconds. Spectral acceleration of the earthquake corresponding to this value is above the design spectral acceleration value for 10% probability of exceedance in 50 years. The convective period of the tank damaged by the sloshing effect, 2.5 seconds. Spectral acceleration of the earthquake corresponding to this value is above the design spectral acceleration value also in addition. Here another facility was the plant with maize storage silos in Nurdağ. Here we saw steel silos both on the ground, supported on the foundation and supported on the columns. Again, different types of damage were encountered. I will try to present these damages. There are silos here whose walls were torn due to internal pressure during the earthquake and whose anchors attached to the foundation were damaged. Here we see similar damage caused by insufficient anchorage strength. Here in the first picture there is a silo whose anchorage could not resist the tensile forces and bolts fell down. In the second row of pictures, the anchors connecting the columns to the ground were again unable to bear the tensile forces and silo fell over. In the third picture, concrete breakout damage is seen in the steel concrete connection under the influence of high tensile forces. In the last picture, we see the corn maize spreading around. The bracing element of the silo is buckled. Here we can see steel bolts breaking off and falling. Pull-out damages occurred under the influence of tensile forces. Some calculations have been carried out regarding anchorage. There are 24 bolts around the silo circle. The filling ratio is stated to be 90%. The total mass was found and the base shear force value was obtained with the help of seismic code. Periodos is approximately 0.68 seconds and shear force and overturning moment were calculated accordingly. Here the shear force and tensile force corresponding to each anchorage bolt were calculated. As can be seen from the right table, it was observed that anchorage bolts were clearly unable to carry the tensile forces at high filling ratios. There is no problem especially in shear force, but tensile force resistance remains low. It was observed in the field that the anchorage bolts failed due to tensile force, not shear force. This situation was also determined by these calculations. Wall openings also occurred in the silos. It has also been proven that the bolts in the wall have insufficient strength. 150 bolts with a diameter of 6 mm were placed at 10 cm intervals along the 15-meter wall. Static and dynamic interior wall pressures were calculated with the help of Eurocode and publications in the literature. As seen in the table, these values were calculated according to the different filling levels. For 90% filling level, the forces in the dynamic situations are around 6 times the forces in the static situation. And the strength of these anchorages was insufficient and the wall opened. Here are the geometric features of the relevant silo and period values according to the filling level. For high level, period values are higher than 0.65 seconds. When looking at the acceleration spectra again at these values, it is clearly seen that the spectral values of the earthquake are higher than the values provided by the seismic code. Conclusion for the main storage silos. In the main storage facility, wall damage was observed in many silos due to the earthquake and internal pressure of the maze contents, and the walls were opened in some of them. For this reason, stored product was scattered around. Anchorage damage was observed in some silos. With the help of the calculations, it has been clearly seen that anchorage used in the silos don't have sufficient strength against especially tensile forces at 50% and 90% filling ratio. Shear forces can also be critical at high filling level and for using insufficient bolt diameter. For this reason, it is recommended to use more than one and high diameter anchorage bolts in each anchorage zone. Another common industrial structure is prefabricated structures. These structures were examined in the İslahiye district of Gaziantep and Kırıkan district of Hatay. The structures are examined in İslahiye can be seen here. Damage such as damage to column beam connections, infill wall collapses, and column hinges were mostly observed. The pictures here are from İslahiye. Here too there are structures examined in Kırıkan. It is seen that the lower ends of the column was hinged. Similar damages. Here the displacement demand of the earthquake is seen. Due to the high displacement demand, damage occurred in the prefabricated structures and columns became hinged. Below and the right is part of another building, pre-earthquake, before earthquake and after earthquake situation. After the earthquake, this frame collapsed in the east-west direction. It is understood that displacement demand of the earthquake was high, especially in this direction. We can see the high earthquake displacement demand. Here, conclusion for prefabricated structures. There are 1 or 2 story prefabricated reinforced concrete buildings in Hatay and Gaziantep industrial zones. Typical spans are 15 to 25 meter height, is around 7 to 10 meter. Press-stressed beams are supported on column cantilevers. Damage occurred in a building in İslahiye when a beam fell. Joint damage is common. It is thought that failure begins in the connection zones under the effect of horizontal load. There are similar damages in Kırıkan. In fact, hinges have occurred at the lower ends of some columns. In general, such structures didn't perform very well in earthquakes. Seismic effects have not been adequately considered at the lower ends of columns and column beam connections. Columns in pin-supported frames were damaged and subjected to excessive horizontal displacement demands. Finally, another type of building, low-rise steel structures. There was a lot of same type of steel structure damage in the Antakya small industrial site. Since the stiffness of the structure was very weak in one direction, large drifts occurred in that direction also. Some examples are shown here. Similarly, there is similar damage here as well. These examples can be increased. Here, low-rise steel structures suffered severe damage in the earthquakes examined. Reasons for these damages include failure to design against seismic effects and poor workmanship. However, it has been understood from the investigations that the earthquake was severe in the area where the small industrial site is located. In here figure, the acceleration response spectrum of the region and the acceleration spectrum values of the earthquake are compared. As seen from the graph, spectral acceleration values greatly exceeded the design values in a large part of the period axis. The 3124 accelerometer station is very close to the location of this region. Finally, recommendations. It has been observed that the seismic fault conditions were exceeded in time damage. Spectral acceleration values expected in the region are below the values occurring in the earthquake. It would be good if the provisions were reviewed. Also, to increase the elastoplastic buckling limit, a hybrid FRP system consisting of glass and carbon is recommended in the literature based on advanced finite element analysis. Also, it is crucial to design the appropriate anchorage for the overturned tank. It has been determined through calculations that earthquake calculations are not taken into account in base and wall anchorage in maize storage silos. There was no problem for the static situation, but the anchorages were insufficient in the dynamic situation. It is significant that the anchorage design should be made according to the seismic forces. Low-rise steel industrial buildings were structures that didn't receive engineering services. For this reason, it is normal for damage to occur. Bracing elements can be used to increase stiffness. Additionally, soft soil was common in this region, and this was not taken into account. It is important that welded and bolted connections are designed to withstand seismic loads. In precast structures, beams collapse in the pins, column beam connection points. The infill walls have been demolished. Hinges have occurred in the columns. In addition, the three-dimensional nature of the seismic motion was not accommodated by any orthogonal links between the two-dimensional portal frames and by properly sized tie beams interconnecting the discrete circuit foundations. This study was financially supported by the TÜBİTAK project, investigation of structural damage caused by near fault and soil effects in the Hatay region following the earthquakes in Kahramanmaraş. We thank to TÜBİTAK, we thank to İstanbul Teknik Üniversitesi and AFAD. Here are our references. And thanks for the listening.
Thank you for the presentation. We may have one question or comment.
Thank you very much. Is my presentation, and maybe the certain perspective you compare the expected association. So I have translation. So this time something really amazing, and so concerning do you have a success to advance event or technical guideline?
Sorry, I can't hear from
So you detect the damage example industrial field, and so I think after this aspect, what relation order software to devise such a tool for updating the guideline.
Can I come near you?
Yeah.
Sorry.
Okay, thank you for your attendance. Now it's lunchtime. The session is over and thank you for everything.
Good afternoon. Sorry for keeping you all in a pause moment. It's a great pleasure for me today to chair the session and to lead it by